A spacecraft bound for Mars can be in danger without ever suffering a collision or an explosion. It may remain on course, its power systems still functioning, and the crew going about their daily routines as usual, while behind the metal panels, the systems keeping them alive have already begun to weaken. A pump may need to run longer to complete the same task. A filter may require replacement earlier than expected, and two sensors that once produced matching readings may slowly begin to disagree. These changes are too small to trigger an alarm, but if they continue to build throughout a long journey, they could gradually reduce the spacecraft's ability to recover from failure. Welcome to Night Cosmos Sleep. In today's journey, we will explore what is most likely to fail first during a years-long mission to Mars. But the more important question is whether, after that first failure, the spacecraft will still have enough water, spare parts, energy, and remaining options to continue. To find the answer, we will begin with signs so subtle that they can remain hidden for a very long time before anyone notices. Many months have passed since the spacecraft left Earth. The planet behind it is now only a small point of light in the deep darkness, while Mars is still too far away to appear as a real destination. No asteroid blocks the flight path, the hull does not shudder from an impact, and the control panels inside the cabin remain filled with green readings. The engines continue making orbital corrections on schedule, power is distributed steadily, and the crew begins each workday according to a familiar rhythm. Food is heated and secured to the table, navigation data is checked, and exercise equipment begins running to slow the loss of muscle and bone in microgravity. From the outside, the mission is still unfolding exactly as planned. Nothing suggests that the spacecraft is moving toward a dangerous condition. The changes appear only in the smallest details behind the technical panels. The latest water processing cycle took 3 minutes longer than before. The amount of clean water recovered was slightly lower than the previous week, but by so little that it could be dismissed as measurement error. Two temperature sensors mounted close together no longer produce exactly the same readings, while a ventilation fan has developed a deeper sound, even though the display still reports a normal rotation speed. No device has stopped working, no reading has crossed an acceptable limit, and there is not yet any reason to activate an emergency procedure. That state, not yet serious enough to demand action, creates the most difficult problem. When a failure is obvious, the crew knows what to do. When everything is still functioning but no longer performing as well as before, they must decide whether the change is only temporary or the first sign of a long decline. Machinery does not exist in only two simple states, working or broken. Between those points, there is often a long period when a device still completes its task but requires more time, consumes more power, or produces less stable results than it once did. A pump may still move water through the pipes, but a slight drop in flow means the motor must run longer to compensate. A filter continues cleaning the air, yet each processing cycle takes more time. A valve still opens on command, only a few seconds more slowly. A sensor continues sending data at regular intervals, even though its readings have begun drifting away from reality. Silent deterioration does not arrive with an explosion, a flash, or an alarm. It often begins with a small increase in power consumption, a slight rise in temperature, a change in vibration, or a mechanical sound that no longer matches its familiar rhythm. Over the course of a single day, these signs may seem almost meaningless. After thousands of cycles, however, they can begin to change the way the entire spacecraft uses energy and resources. When a pump must run longer to maintain the same flow rate, it consumes more electricity, and that energy eventually becomes heat. The cooling system must work harder to remove that heat from the equipment compartment, while shafts, bearings, and seals remain under friction for longer during every cycle. An unstable flow can also place a different load on the filter than the original design anticipated, shortening its useful life. A very small change in one pump gradually transfers stress to equipment that had no problem of its own. This is how a spacecraft grows old while still appearing normal. It does not immediately lose function. It simply has to work harder to maintain the same condition, much like a body that continues performing its daily tasks, even though the organs inside are no longer as healthy as they once were. Choosing the right time for a repair is difficult because equipment life rarely declines along a straight, predictable line. One component may operate steadily for months, then deteriorate quickly once its lubricant thins or a seal loses elasticity. Another may weaken very slowly, leaving vague signs for a long time without ever stopping completely. Replacing a part too early means discarding a component that may still have thousands of useful hours remaining, and on the way to Mars, that mistake does more than increase cost. A spare part used today may be the only one available later in the mission. Waiting too long carries its own risks, because a weakening device can draw healthy systems into the same chain of wear. A hotter motor causes internal materials to age faster. A seal that gradually hardens can develop a small leak. Gas entering a liquid line can make pressure fluctuate and sensor data harder to interpret. By the time the failure becomes obvious, the crew may no longer be repairing a single pump. They may be dealing with an entire network of problems that has formed around it. The spacecraft operates almost like a living body built from metal, wires, and pipes. Pumps keep water and cooling fluids circulating, performing a role similar to the heart. Fans move air through the cabin and into processing equipment, doing work much like the lungs. Filters remove waste, impurities, and compounds that should not remain in the living environment, serving a function close to that of the liver and kidneys. Sensors form the nervous system, continuously tracking temperature, pressure, flow, vibration, electrical current, and atmospheric composition before sending everything to the central computer. From thousands of separate numbers, the computer assembles a picture of the spacecraft's health, yet it cannot look directly inside a pipe, touch a motor, or hear the change in a fan's sound. Everything the system knows depends on the signals provided by its sensors. If a flow sensor reports a value lower than the true rate, the crew may assume the pump is weakening and increase its power to restore the flow. The motor must then work harder, generating more heat and wearing down faster, even though the original problem exists only in the sensor. The opposite situation may be even more dangerous, when the display continues to report normal conditions while the true flow has already declined. The deterioration can continue unnoticed until its effects appear somewhere else, perhaps as longer water processing times, a filter that becomes dirty too soon, or an increased load on the cooling system. A spacecraft traveling far from Earth needs more than durable equipment. It must also recognize which component is deteriorating, which signal is merely noise, and which small change could begin a much larger chain of risk. When that ability to recognize its own condition starts to weaken, a vehicle that remains physically intact may begin to lose its understanding of what is happening inside itself. Experience aboard the International Space Station shows that this problem does not exist only in engineering plans. Over many years of operation, pumps, fans, valves, and seals on the ISS have provided real-world data on how hardware ages in space. A 2026 NASA report described 6 pump assemblies in a thermal circulation system. 3 had already required replacement, while 2 others showed signs of deterioration. What stands out is that devices serving the same function do not necessarily fail in the same way. One assembly may show changes in vibration, while another consumes more power or gradually loses the ability to maintain flow. A future Mars spacecraft will not use the exact same hardware found on the ISS, but the data still serves as a reminder that moving equipment truly does age in space, and the path toward failure does not always match the original predictions. Before launch, engineers can run pumps for thousands of hours, expose materials to repeated heating and cooling cycles, and apply vibration and pressure to simulate mission conditions. Even so, a laboratory cannot fully reproduce a long operating environment in which microgravity, real wastewater, radiation, maintenance activity, and many chemical reactions occur at the same time. Deposits that never appeared during testing may form after months in flight, while a material expected to remain flexible for years may harden sooner after contact with a compound that was never considered. The service life written into a design is not an absolute promise. It is only an estimate based on what humans already know, while a real mission always contains conditions that cannot be completely predicted. Inside the cabin, the work schedule continues. The steady sound of fans moves through the walls, the displays show no warnings, and water still passes through the pipes as it has during every previous cycle. Only the operating time has grown slightly longer, power consumption has risen by a barely measurable amount, and the remaining service life is being taken away in increments too small to notice. The pump may become the first device to fail, but it is also possible that the pump will continue working properly, while the flow sensor has already begun drifting away from the true value. At that point, the problem no longer belongs to a single component. It lies in the spacecraft's ability to understand the condition of the entire system. To understand which part is most likely to weaken first, we must look more deeply at what the spacecraft is trying to keep stable. Its mission is not simply to carry people across the distance between two planets. Behind its metal walls, it must continuously preserve water to drink, air to breathe, a suitable temperature, and pressure safe enough for life. In the emptiness between worlds, where there are no rivers, winds, or atmosphere, the spacecraft is trying to keep a small piece of Earth alive. Outside the spacecraft's windows, there is no air to draw in, no river from which to pump water, and no wind strong enough to carry excess heat away from the cabin. The space surrounding the vehicle is nearly empty, cold, and incapable of supporting life in any natural way. On Earth, a stuffy room can be ventilated by opening a door, a broken water line can be repaired by a maintenance crew, and heat from machinery can eventually pass into the air, the walls, or the surrounding environment. A spacecraft bound for Mars receives none of that assistance. Everything the crew breathes, drinks, releases, and warms must be captured, processed, and returned to use within an enclosed space protected by only a few layers of material. The living environment inside does not sustain itself simply because the hull has been sealed. If a closed room were placed in space, oxygen would gradually be consumed, carbon dioxide would rise, water vapor would collect on surfaces, heat from bodies and equipment would build up, and waste would continue to accumulate. The cabin might retain its shape, but it would quickly become uninhabitable. To transform a metal compartment into a place where people can live, the spacecraft must continuously perform tasks that, on Earth, are handled by the atmosphere, the oceans, water supply networks, waste treatment facilities, and countless natural processes unfolding around us that we rarely notice. NASA calls the network responsible for this work the Environmental Control and Life Support System, usually shortened to ECLSS. The name may sound technical, but its meaning is fairly simple. It is the complete system that allows people to breathe, drink water, regulate body temperature, and live safely inside a spacecraft. It is not a single machine sitting in one corner of the cabin and creating every condition needed for life. Many different devices must work together continuously, including water recovery units, air processing equipment, oxygen generators, ventilation fans, humidity controls, pressure regulation networks, waste management systems, and sensors that monitor the cabin. Smoke detection, fire risk control, and the prevention of contaminant buildup are also part of this network. Most of its operation can be understood through three closely connected cycles. Water is recovered from cabin humidity, sweat, breath, urine, and other waste streams, then sent through purification. Air must have carbon dioxide removed, oxygen restored, and unwanted compounds filtered out of the enclosed environment. Heat produced by human bodies, computers, lighting, and technical equipment is transferred into the cooling system, then carried to a place where it can be released into space. These three cycles are often described separately because that makes them easier to explain, but aboard the spacecraft, their boundaries are not truly distinct. A change in one almost always affects the other two. Clean water can be sent into an electrolysis system to produce oxygen for the crew. That process requires electricity, and electricity passing through machinery creates additional heat. The new heat must then be carried away by cooling fluid, forcing pumps and radiators to continue working. If water recovery begins to decline, the spacecraft loses not only drinking water but also part of the raw material needed to generate oxygen. When electrical power is limited, the oxygen generator, pumps, and water processing system may all have to change the way they operate. No component truly stands alone. The entire living environment depends on a balance between streams of matter and energy that continually pass through one another. This is why a technical failure may appear somewhere far from its original cause. A drop in oxygen could lead the crew to suspect the electrolysis unit, while the real problem may have begun with an insufficient supply of clean water. A rise in cabin temperature does not necessarily mean the radiator has failed, because a weakening pump may have slowed the circulation of cooling fluid. High humidity may not come from the dehumidifier at all. The cause could lie in a water processing branch that has temporarily stopped, or in a ventilation fan that is no longer distributing air evenly. Diagnosing problems aboard the spacecraft therefore becomes a process of tracing clues through a network, where the same symptom can have several different causes, and a small failure in a hidden location can gradually spread into areas that seem unrelated. Air provides the clearest example of this dependence. On Earth, warm air usually becomes lighter and rises, while cooler air sinks, creating natural convection currents that keep the air in a room moving. Microgravity changes that process significantly. A breath leaving the mouth does not naturally drift toward the ceiling, and the carbon dioxide released by the body can remain around the head if ventilation is not strong enough. Someone sleeping or working in an area with poor circulation may begin breathing in part of the air they have just exhaled, even while the average oxygen level across the cabin remains safely above the danger threshold. The fan hidden behind the wall therefore does much more than make the cabin feel comfortable. It continuously draws air away from the areas occupied by the crew, dilutes the carbon dioxide, and carries the airflow toward the processing system. Once its composition has been adjusted, the air returns to the cabin through other vents. If the fan slows down, an intake becomes blocked by a storage bag, or the airflow changes direction after a panel is opened for maintenance, the air quality around an individual crew member may deteriorate before a sensor somewhere else detects it. The cabin may still contain enough oxygen when measured across its entire volume, while the air near someone's face is less healthy than the average value displayed on the screen. Pressure must also be monitored continuously. The spacecraft may be sealed, but no system is completely free from loss. Connections, valves, hatches, and seals can all allow very small amounts of gas to escape. On Earth, such leakage can be replaced by air from the surrounding environment. In space, every molecule that escapes leaves the system and does not return on its own. The spacecraft must determine whether the rate of loss remains within acceptable limits while maintaining enough stored gas to replace what cannot be recovered. Humidity must be kept within a suitable range because the human body continually releases water vapor into the cabin through breathing and perspiration. If humidity rises too high, water can condense on cold surfaces, seep into electrical equipment, or create favorable conditions for microorganisms to grow. Air that is too dry can irritate the eyes, skin, and respiratory system, leaving the crew more fatigued during a long mission. The water removed from the air is not discarded. It is sent back into the processing system, becoming another link in the water cycle. After passing through several layers of purification and inspection, moisture from a person's breath may eventually return as drinking water. Heat is less intuitive because the space outside is extremely cold, yet the spacecraft cannot simply open a door to cool itself. In a vacuum, there is almost no air to carry heat away through convection. Energy produced by human bodies, computers, and equipment must be absorbed into circulating fluid, carried through pipes, and delivered to radiator panels outside the spacecraft. Only then can the heat leave the vehicle as radiation. If the fluid begins moving more slowly or the radiator surface loses efficiency, excess energy will start accumulating inside the cabin. Even a perfectly functioning power supply can become a problem when the heat it produces no longer has an effective path outward. The life support system must also manage less visible concerns such as odors, dust, volatile compounds released by materials, bodily waste, and the risk of fire. New objects brought into the cabin may release small amounts of chemicals. Cooking or warming food creates additional vapor and fine particles. Human skin is constantly shedding, hair falls out, and fibers from clothing join many other fragments that do not settle onto the floor as they would on Earth, but instead drift with the airflow. Fans and filters must capture them before they collect on sensors, enter equipment, or gather in places that are difficult to reach. A flame in microgravity also lacks the familiar shape seen on Earth. Hot gas does not rise in a fixed direction, so a flame may become more spherical, while smoke does not naturally collect near the ceiling. Ventilation continues to determine where the smoke travels, and fire detection equipment must recognize changes in the environment before the crew can see the danger. If the fire must be extinguished, the spacecraft cannot pour large amounts of water over electrical equipment or open a door to let the smoke escape. Every response must take place within the same enclosed environment the crew will still need to inhabit after the emergency has passed. These functions remain so quiet that the crew often notices them only when something changes. Normal air has no distinctive sound. Clean water appears at the dispenser without revealing the journey it has just completed. Heat leaves the cabin without creating any obvious sensation. Life aboard the spacecraft is sustained by thousands of small actions, repeated continuously behind the walls, where valves open, fans rotate, fluids move, and sensors examine every change. The spacecraft may carry stored oxygen, water tanks, and emergency supplies for moments when the primary systems encounter trouble. A journey lasting many months, however, cannot rely entirely on what was loaded before launch. The required mass would become too great, while every kilogram carried aboard demands additional fuel and space. Most resources must be recycled, meaning that the same water, air, and cooling fluid will pass through the system thousands of times. Throughout that process, pumps age, filters accumulate impurities, sensors gradually lose accuracy, and materials endure countless thermal cycles. This is what makes a miniature Earth different from the real planet. Our world has vast oceans, an immense atmosphere, and countless natural cycles capable of absorbing small disturbances. Inside a spacecraft, resources are far more limited, and every cycle depends on a finite piece of equipment. A small imbalance cannot dissolve into an entire planet. It must be detected, corrected, and compensated for before it spreads. Within this network, water is the easiest resource to follow because it can be seen entering a cup, leaving the body, and returning to the system. Yet water aboard the spacecraft does not remain quietly inside a tank, waiting to be used. It moves continuously through the crew, the cabin air, pipes, filters, and processing chambers, repeating the same journey many times throughout the mission. The drop of water in a cup today may have been part of someone's breath, perspiration, or wastewater yesterday. And to become clean again, it must pass through a chain of equipment that cannot remain inactive for very long. The next part of our journey begins with that single drop of water, because aboard a spacecraft bound for Mars, it may need to survive and circulate longer than almost any other part of the mission. Water flows from the valve for only a few seconds, gathering into a floating sphere before being drawn into an astronaut's mouth. In that moment, it looks like any sip of water on Earth, clear, odorless, and revealing nothing of the long journey that brought it back to the cup. Some of it may once have been stored in a reserve tank, but it may also have been part of the crew's breath, perspiration, or urine only a few days earlier. After passing through the body, its journey does not end by disappearing from the spacecraft. Moisture is removed from the air, wastewater is collected, impurities are separated, and the remaining compounds undergo further treatment before the water quality is tested and returned to clean storage. If the results do not meet the required standard, the water must re-enter the system and begin another cycle. On Earth, water seems to be everywhere around us. It exists in rivers, lakes, underground reservoirs, clouds, and oceans, moving through cycles so vast that the amount lost by a single household is almost insignificant to the planet as a whole. A spacecraft bound for Mars has no such enormous reserve. Every kilogram of water brought aboard increases launch mass, occupies space, and requires additional fuel. If the crew simply used water and discarded it, the amount that would need to be carried from Earth would quickly become overwhelming. A more practical solution is to keep it within a closed loop, where the same resource is recovered, purified, and used repeatedly throughout the journey. Water passing through the human body does not return to the system in a single form. Breath and perspiration raise the humidity inside the cabin, and environmental control equipment removes that vapor from the air by cooling it until it condenses. Urine is directed into a separate processing branch because it contains higher levels of salts, organic matter, and compounds that are more difficult to remove. Water used for hygiene and daily activities carries different substances as well, requiring the system to recognize the incoming source and apply the appropriate treatment. Even after most impurities have been separated, the water cannot be sent directly back into a cup. Additional stages must remove the remaining dissolved compounds, control microorganisms, and confirm that the final quality falls within safe limits. This is not a process in which one filter alone transforms dirty water into clean water. A filter can capture solid particles, but many dissolved substances will pass straight through it. Microorganisms small enough to cross certain layers of material may also remain, while organic compounds require other methods to break them down or remove them. The entire treatment loop operates like a series of inspection gates, with each stage responsible for a different group of problems. Water is accepted only when the final results show that it is safe enough to return to storage. If a sensor detects an abnormal value, the water may be held back or redirected for further treatment, forcing pumps, filters, and testing equipment to continue working. In 2023, NASA announced that the system aboard the International Space Station had demonstrated an overall recovery rate of nearly 98% for the water entering the recycling loop. Before equipment was added to process the concentrated brine left behind, the total recovery rate generally remained around 93 to 94%. The improvement did not come from replacing the entire system, but from extracting additional water from the dense waste stream that had previously been difficult to process any further. This achievement is especially important for deep space missions because a difference of only a few percentage points can determine how much additional water the spacecraft must carry when it leaves Earth. If 100 liters of wastewater enter the system, a recovery rate near 98% means that roughly 98 liters can be returned to use. The remaining 2 liters may not sound like much, but that figure should not be understood as a guarantee that water can last forever. Every real recycling loop contains some portion that cannot be fully recovered. Water may remain trapped in concentrated waste, be lost during filter replacement, stay inside pipes, or escape through extremely small leaks. Cleaning, research, and repair activities may also consume water that does not immediately return to the cycle. As the mission continues, these small losses accumulate, gradually reducing the reserve unless they have been accounted for in advance. The figure of 98% also describes system performance under particular operating conditions. It does not answer every question about durability. Equipment may achieve extremely high efficiency during testing or throughout its first months of operation, but a journey to Mars requires that performance to continue through thousands of consecutive cycles. Filters gradually collect impurities, exchange surfaces may become coated with deposits, pumps accumulate more operating time, and treatment chemicals continue to be consumed. The quality of incoming wastewater is not exactly the same every day, because the crew's diet, health, medications, and activities can all alter its composition. High efficiency matters only while the system remains healthy enough to sustain it. A pump with reduced flow will lengthen processing time. A dirty filter may create additional resistance, forcing the motor to consume more electricity to push water through it. A seal that has lost its elasticity can begin to leak, while a slow valve may prevent the flow from reaching the right place at the right moment. These changes may not make the water immediately unsafe, but they gradually narrow the operating margin. A cycle that once took 1 hour may begin lasting several minutes longer, then many minutes longer, until the system no longer has enough time to process all the water the crew produces each day. Experience aboard the ISS has shown that the distance between design expectations and real operation can sometimes be greater than anticipated. Reports on its water systems have documented valves that did not achieve the expected reliability, leaking seals, and contaminants that shortened the service life of components. Some substances present in real wastewater also created deposits or chemical reactions that had not been fully predicted during testing on the ground. These problems did not cause the entire system to collapse at once, but they required the crew to replace parts, adjust procedures, and rely on regular support from engineers on Earth. The International Space Station has an advantage that a Mars spacecraft will not. Replacement parts can be prepared for the next cargo mission. Specialists on the ground can monitor data continuously, and the crew can receive detailed repair procedures within a relatively short time. During an interplanetary journey, every filter, seal, chemical supply, and tool must be selected before launch. A single unexpected contaminant could increase the frequency of filter replacements, consuming a spare parts supply intended to last for years much earlier than planned. The system may continue producing clean water, but every effort to maintain that performance will consume another portion of resources that cannot be replenished. Water quality sensors play an especially important role because clear water is not necessarily safe. Many compounds do not alter color or odor at levels the human senses can detect. Microorganisms may also be present long before they produce any obvious sign. The crew cannot simply taste the water and decide whether it meets safety standards, so they must rely on instruments that measure electrical conductivity, chemical composition, and other indicators of quality. Deposits forming on a sensor's surface can slow its response or gradually cause its readings to drift away from reality. When an abnormal result appears, the spacecraft must decide whether to run the water through another cycle, test a sample manually, or temporarily keep that supply out of the clean water tank. Repeating the treatment process may sound like the safest choice, but it comes at a cost. Pumps must run longer, filters receive an additional load, more electricity is consumed, and more heat is produced. If the sensor is simply giving a false reading, the spacecraft has spent valuable resources reprocessing water that was already safe. If the warning is ignored while the water truly fails to meet standards, the contamination could spread into the entire storage tank. The most difficult question is not whether the system is capable of purification, but whether it can correctly recognize when more treatment is needed. Water is also connected to nearly every activity inside the cabin. The crew needs it for drinking, preparing food, and maintaining personal hygiene. Some of it is used in medical procedures or scientific research. Fluids also help control temperature, while clean water can be electrolyzed to produce oxygen. When the water reserve begins falling faster than expected, the effects extend far beyond thirst. The spacecraft may have to limit hygiene, change the way meals are prepared, reduce certain research activities, or adjust the operating mode of the oxygen generation system. A single resource begins to shape both the crew's daily schedule. Reserve water is always carried to protect the crew during periods when the recycling system is offline. That reserve, however, cannot be unlimited. Carrying too much water from Earth would greatly increase the spacecraft's mass. Carrying too little could leave the crew without enough time to complete repairs during a prolonged failure. Engineers must balance the initial water supply, recovery efficiency, repair capability, and acceptable loss rate. Every decision depends on assumptions about how long pumps can operate, how long filters will last, how much leakage will occur, and how often failures are likely to happen. If reality differs from those predictions in only a few places, the safety margin for the entire mission will begin to shrink. The greatest concern is not a water tank suddenly running dry. A more dangerous decline may happen so slowly that each individual day still appears normal. This week, the recovered volume is only slightly lower than it was the week before. The following month, a filter is replaced a few days earlier than planned. The processing cycle takes longer, but it still finishes before the clean water reserve falls too low. No single reading is dramatic enough to create a crisis, yet the overall trend has already begun to change. If the spacecraft detects it early, the crew still has time to search for leaks, clean the pipes, or adjust the procedure. If the shift is hidden by sensor error, the reserve may fall significantly before the true cause is discovered. Inside the equipment compartment, water continues moving through the pipes. Pumps begin turning, the flow passes through each treatment stage, and its quality is checked before it returns to the clean tank. No one sees each molecule come back, yet the entire mission depends on this process being repeated reliably. The drop inside the cup does not need to remain intact throughout the journey. It is continually separated, mixed, and redistributed among many different sources. What must outlive the mission is the ability to recover it, because as long as the cycle continues to function, the spacecraft can reclaim water that has passed through the human body and return it to use. A recovery rate approaching 98% shows how far humanity has come in building a miniature water cycle in space. That figure does not eliminate wear, limited spare parts, or unexpected substances entering the system. The success of a long-duration mission depends not only on how much water can be recovered on the system's best day, but on whether recovery can remain high enough after years of operation, even when pumps have aged, filters have been replaced many times, and sensors are no longer as new as they were when the spacecraft left Earth. Water can be reclaimed from breath, perspiration, and waste, then returned to the cup after an almost closed journey. To sustain life, however, the spacecraft must also manage what the crew releases with every breath. Each time oxygen enters the lungs, carbon dioxide, water vapor, and heat return to the cabin. The water cycle can recover the drops that were lost, while the air cycle must continuously repay the debt created during every minute that human beings remain alive inside the spacecraft. In a crowded room, the air often begins to change before anyone understands why. After several hours, the initial sense of comfort gradually fades, eyelids grow heavier, a dull headache begins to form, and even following a simple conversation becomes more difficult. On Earth, that room is still connected to the vast atmosphere outside. Fresh air can enter through doors, windows, ventilation gaps, or an air conditioning system, while the gases people exhale are diluted within a much larger volume. Inside a spacecraft bound for Mars, that natural exchange does not exist. The cabin is an enclosed space, where every crew member continuously draws oxygen from the same atmosphere and returns carbon dioxide, water vapor, and heat. Nothing disappears on its own, and there is no nearby external atmosphere to replace what has been consumed. Every minute the crew remains alive changes the composition of the air. Oxygen enters the lungs and takes part in the process that allows the body to release energy from food, after which carbon dioxide returns to the cabin through each exhaled breath. Water vapor leaves with the airflow, while body heat continues warming the environment. If the spacecraft simply kept the air sealed without processing it, oxygen would gradually decline as carbon dioxide and humidity increased. The living space would still retain its pressure, the hull would remain intact, and the walls would still be sealed, yet the atmosphere inside would slowly move beyond the range that is safe for human life. This is why maintaining breathable air is far more complicated than carrying a few tanks of oxygen. The spacecraft must remove carbon dioxide, generate or replenish oxygen, control moisture, filter unwanted compounds, and keep air moving through every area occupied by the crew. These tasks continue quietly in the background and receive almost no attention while the system is working properly. The crew hears only the steady sound of fans behind the walls and feels a gentle current passing through the vents, but beneath that familiar sound, an entire network is restoring the atmosphere after every breath. Carbon dioxide must be drawn out of the cabin before its concentration rises too far. Air is directed through materials capable of trapping the gas, and the treated air is then returned to the living area. Depending on the design, the absorbing material may be regenerated by changing the pressure or temperature, or by removing the captured carbon dioxide from the circulation loop. The process sounds simple when described in only a few sentences, but in practice, it depends on fans, valves, air ducts, sensors, and electrical power. If the airflow slows or the treatment material gradually loses efficiency, less carbon dioxide will be removed from the cabin during each cycle. Oxygen can be carried in storage tanks, but a long-duration mission cannot survive solely on what was loaded on Earth. The mass required for many months or years would become too great, especially when water, food, scientific equipment, and repair supplies must all travel on the same spacecraft. A more practical approach is to regenerate oxygen from resources already available on board, with water playing a central role. When an electrical current passes through water inside an electrolysis unit, the molecules are separated into oxygen and hydrogen. The oxygen enters the cabin atmosphere to replace what the crew has consumed, while the hydrogen can take part in another process that recovers additional water from carbon dioxide. The air and water cycles therefore do not exist as separate systems. Clean water supplies the raw material used to generate oxygen, while carbon dioxide from the crew's breath can participate in a reaction that returns some water to the recycling loop. Electricity powers these processes, but electrical equipment creates heat, and that heat must be carried away from the cabin by the cooling system. If the water cycle begins to weaken, the supply available to the oxygen generator is also affected. If electrical power must be conserved, the spacecraft may be forced to reduce the output of its air processing equipment. When the cooling system performs poorly, accumulated heat places the electrolysis unit and its sensors under even less favorable operating conditions. The life support network has no single center that can simply be replaced to make every problem disappear. The water recovery system reclaims water. The oxygen generation system uses some of that water to produce oxygen, and the air revitalization system removes carbon dioxide and other unwanted substances from the cabin. Separate names help engineers divide their functions, but the crew survives through the coordination of all three. A problem in one branch may appear as a symptom in another, making diagnosis far more complicated than reading a single value and replacing the device with the matching name. A rising carbon dioxide level is the clearest example. The first reaction may be to suspect the removal unit itself, but the true cause does not necessarily lie there. A ventilation fan may be turning too slowly, preventing enough air from reaching the processing chamber. An intake vent may have become partly blocked by a storage bag, securing strap, or another object after the cabin was rearranged. The crew may have just completed an intense exercise session, temporarily producing more carbon dioxide than usual. A change in temperature may reduce the efficiency of the absorbing material, while the gas sensor may have begun drifting away from the true value. The same rising number on a display can emerge from several entirely different chains of causes. Even a modest increase in carbon dioxide should not be considered harmless. People do not need to suffocate or lose consciousness before feeling its effects. Long before the concentration reaches an obviously dangerous level, the body may already experience headaches, drowsiness, fatigue, and reduced concentration. In ordinary life, that discomfort might simply make work slower. Aboard a spacecraft, it directly affects the crew's ability to read procedures, compare data, and perform precise technical operations. Place this situation at a moment when the crew is trying to determine why the water processing system has begun operating more slowly. They must identify the correct pipe, close the valves in the proper sequence, and remove an equipment assembly within a cramped space. The carbon dioxide level is not high enough to trigger an emergency alarm, but the person performing the repair already has a headache and is struggling to remain focused. Overlooking a single line of instructions, selecting the wrong connection port, or forgetting to check the pressure before opening a panel could turn a manageable repair into a far more complicated problem. This creates a quiet feedback loop between humans and machinery. A weakened air system slightly reduces the crew's cognitive performance, and that decline makes it more difficult for them to diagnose and repair the system accurately. Both sides continue to function, but neither remains at its best. The danger does not appear as one dramatic moment. It accumulates through a series of small decisions made under conditions that are slightly less favorable than normal. The distribution of air inside the cabin is just as important as its average composition. On Earth, warm air usually rises while cooler air sinks, creating natural convection that continually mixes the atmosphere. Microgravity profoundly changes that familiar process. A breath leaving the mouth does not automatically drift toward the ceiling, and carbon dioxide can remain around the head if ventilation is not strong enough. Someone sleeping in a corner of the cabin may breathe in part of the air they have just exhaled, even while a sensor in the center of the compartment reports that the average composition remains within acceptable limits. Ventilation fans, therefore, become essential components rather than devices that simply make the cabin feel comfortable. The airflow must draw carbon dioxide away from the area around the face, carry it to the processing equipment, and distribute clean air back into the living space. If a fan slows by only a few percent, the change may not immediately raise the carbon dioxide level throughout the entire cabin. Instead, poorly ventilated pockets may first develop in corners, behind storage bags, or around sleeping areas. Air quality becomes uneven, while the monitoring system can see only the data collected at the locations where its sensors are installed. Opening a panel during maintenance can also alter the direction of airflow. Newly installed equipment may occupy part of a ventilation path, turning an area that once had good circulation into a place where gases begin to accumulate. Changes in cabin layout that seem unrelated to life support can still affect how carbon dioxide is distributed. A crew member may develop a headache in one location, but feel completely normal after moving into another compartment, creating a symptom that is difficult to explain when only average readings are considered. The water vapor released by the human body must be controlled at the same time. Every breath, shower, and exercise session adds more moisture to the cabin. Air that becomes too humid allows water to condense on cold surfaces, enter electrical equipment, and support the growth of microorganisms. If humidity falls too low, the eyes, skin, and respiratory system become dry, leaving the crew uncomfortable over long periods. The system must maintain a balance that keeps people comfortable without creating favorable conditions for mold or bacteria. The water vapor that is collected is not discarded. It returns to the water processing loop, directly connecting each breath to the cup used the following day. When humidity control equipment begins to weaken, the effects spread into both the atmosphere and the recovered water supply. Higher humidity makes the cabin uncomfortable and increases the risk of condensation, while water that is not collected efficiently causes the reserve to decline. A problem in the airflow becomes a problem in the water cycle without a single pipe needing to break. Other contaminants are also produced continuously within the enclosed environment. Plastics, adhesives, coatings, and electrical equipment can release small amounts of volatile compounds. Heated food creates odors and tiny particles, while cleaning products, medications, and everyday activities introduce additional substances into the cabin. On Earth, many of these materials would be diluted or carried outside through ventilation. Aboard the spacecraft, they continue circulating with the air until they are captured by filters or treatment materials. Every filtration layer has a limit. Absorbent materials gradually become saturated. Surfaces collect dust, and the airflow must overcome increasing resistance. Fans are forced to work harder to maintain the same flow, consuming more electricity and producing more heat. If fan speed remains unchanged, less air passes through the system, and fewer contaminants are removed. A weakening filter does not produce only one symptom. Its effects may appear simultaneously in air quality, electrical consumption, and motor temperature. The ability to regenerate oxygen presents another challenge. Current systems have demonstrated that humans can produce oxygen from water and recover part of the resources they have already used, but deep space missions require a much more closed cycle. NASA has established a goal for habitats far from Earth to recover at least roughly 75% of their oxygen, while continuing to study technologies capable of exceeding that level. This percentage is more than a measure of chemical efficiency. It determines how much water, stored oxygen, and other supplies the spacecraft must carry from the beginning. If the recovery rate is low, the oxygen that does not return to the cycle must be replaced from stored reserves. A difference of only a few percentage points, repeated over many months, becomes a significant amount of mass during a long mission. Greater efficiency reduces what must be launched from Earth, but a more complex system also requires additional equipment, valves, catalysts, and maintenance procedures. High efficiency does not automatically mean high reliability. The technology must recover a large share of the oxygen while remaining durable, repairable, and economical in its use of supplies throughout the journey. The reaction that combines hydrogen with carbon dioxide to recover water illustrates this trade-off clearly. It keeps more resources within the cycle and reduces the amount of water and oxygen that must be carried. But it also adds new equipment and operating conditions. The catalyst must remain effective, temperature must be controlled, and the gases must enter in the correct proportions. Any deviation can reduce efficiency or create unwanted products. The technology expands the spacecraft's independence while also adding more components that must be monitored. Stored oxygen remains essential whenever the generation system is shut down for maintenance or suffers a failure. The reserve, however, can protect the crew only for the period anticipated during mission planning. If repairs take longer than expected, the spacecraft may have to reduce physical activity, limit the number of occupied compartments, or adjust the work schedule to lower consumption. Each decision extends the available time, but it also affects health, morale, and the crew's ability to complete the mission. Even the exercise required to protect muscles and bones increases oxygen demand. The crew cannot simply stop exercising for months, because the body would weaken more rapidly in microgravity. They must balance long-term health against the need to temporarily reduce the load on the system. The living environment and the human body constantly influence one another, making it impossible to separate the engineering problem from biology. Inside the cabin, air has no visible shape that the crew can follow with their eyes. Its condition reveals itself only through physical sensations, the sound of fans, and the numbers displayed on screens. When everything works properly, the crew almost forgets that every breath is being processed. Oxygen enters the lungs, carbon dioxide leaves the body, and the system behind the walls quietly restores the composition of the air before it returns again. That quiet stability depends on constant movement. Air must pass through intakes, ducts, filters, and processing chambers. Water must flow into the electrolysis unit. Hydrogen and carbon dioxide must be delivered to the correct reaction chamber. Heat must be carried away from operating components by cooling fluid. Chemistry can regenerate oxygen and recover water, but molecules cannot find their own way to where they are needed. Behind every reaction are pumps moving liquids, fans drawing gases, valves controlling direction, and seals keeping each pathway closed. They repeat the same motions through thousands of hours, enduring friction, heat, and small changes in their operating environment. Every breath leaves behind a debt that the spacecraft must repay with electrical power, filtration materials, and the operating life of its equipment. Water and air can be regenerated many times, but the components that keep them moving cannot run forever without aging. Before an alarm ever sounds, the first sign of change may be nothing more than the lower hum of a fan or an unfamiliar vibration behind a technical. After living for many months inside the same enclosed space, the crew gradually memorizes the sounds of the spacecraft without consciously trying. The steady flow of ventilation fans behind the walls, the sound of valves changing position at fixed times, and the faint vibration passing through a handrail whenever the water processing system begins a cycle all become familiar. At first, these noises blend into a background that is difficult to distinguish, but over time, they become as recognizable as rain falling on a roof or a refrigerator humming in a kitchen. Someone who has lived aboard long enough may notice a change before any abnormal reading appears on a screen, simply because a sound repeated thousands of times no longer follows its usual rhythm. Near the end of a workday, while the cabin is almost quiet, the pump behind a technical panel suddenly sounds slightly deeper. There is no impact, no grinding of metal against metal, yet the vibration traveling through the surface feels different. Pressure remains within acceptable limits, and the flow rate has not fallen far enough to trigger a warning, but the engineer keeps a hand pressed against the equipment housing longer than usual because the sensation is not the same as it was the day before. Pumps, fans, and valves receive little attention when they are working properly, even though nearly every cycle aboard the spacecraft depends on the movement they create. Chemical reactions can separate oxygen from water. Filtration materials can capture carbon dioxide, and control systems can calculate exactly how much fluid needs to be moved, but none of these processes can take place unless the air and water reach the correct location. That task belongs to rotating shafts, fan blades, motors, bearings, and seals that must repeat the same motions for thousands of hours. Every rotation creates friction, even when the surfaces have been manufactured with extreme precision. Heat forms inside the motor and must be carried away. Materials continually expand and contract, and load-bearing contact points experience changing forces during each startup cycle. Space does not eliminate these physical laws. Microgravity may alter some of the loads found on Earth, but it cannot prevent metal fatigue, changes in lubricants, or the gradual loss of elasticity in polymers. A weakening pump rarely begins with the motor suddenly coming to a stop. The first signs usually appear in its performance. The same amount of electrical power may move less water than before, or the device may need to draw more current and run longer to maintain its original flow rate. Small differences can easily be hidden by normal fluctuations in temperature, pressure, and daily water demand. When the crew exercises more, the amount of water collected from cabin humidity rises. When one treatment branch is temporarily shut down for maintenance, the flow through the pump changes. The data therefore never forms a perfectly straight line. Engineers must identify the trend beneath those fluctuations, noticing whether cycle times have gradually lengthened or electrical consumption has steadily increased over several weeks. A single unusual operating cycle may mean very little, but dozens of small changes moving in the same direction can indicate that the motor is working harder to perform a task that was once easy. When flow begins to decline, the control system often compensates by extending operating time or increasing the speed of the device within allowable limits. Enough water is still processed to meet the crew's daily needs, so no shortage is immediately felt. But the cost is transferred elsewhere. A motor that runs longer produces more heat, forcing the cooling system to carry additional energy away from the equipment compartment. Bearings and shafts endure more time under friction, while the insulation around electrical windings remains exposed to higher temperatures for longer than usual. The filter downstream receives water at a different pressure, and valves must adjust more often to keep the system stable. The spacecraft still produces the same amount of clean water, but several components have sacrificed more of their service life to preserve the same final result. This is why a display showing only the volume of water produced can create a false sense of safety. The output still meets requirements, while the hidden process is becoming increasingly expensive in electrical power, heat, and durability. The fluid being transported also affects the machinery in return. Water inside the system is not always like the clean water flowing through household pipes. In waste recovery branches, it may contain salts, organic compounds, fine particles, and substances that vary with the crew's diet or health. Although most of these materials are removed before reaching sensitive equipment, very small deposits can still accumulate in narrow gaps, on valve surfaces, or in areas where the flow is slow. Hard particles passing through a pump impeller create additional wear, while layers of sediment alter the shape of the flow path and force the equipment to work harder. A chemical reaction not fully anticipated during ground testing may produce precipitates after months of operation, and by the time they are detected, the deposit may already be thick enough to affect the flow. The fault does not necessarily lie in the motor or the rotating shaft. The environment the pump must handle may have changed in a way that causes even healthy equipment to perform less efficiently. A similar process occurs in ventilation fans. Dust, fabric fibers, hair, and skin cells do not fall to the floor in microgravity. Instead, they drift with the airflow toward the intake vents. Filters capture most of this material, but as the layer of dust thickens, resistance increases. The fan must produce greater pressure to move the same volume of air through the system, consuming more electricity and raising the motor temperature. If the controller maintains the same rotation speed, airflow will decline, increasing the risk that carbon dioxide will accumulate in poorly ventilated areas. The sound may also change when dust collects unevenly on the blades or the bearings begin to wear. The crew might hear a low vibration, a faint whine, or a repeated fluctuation synchronized with each rotation. Every sound suggests a different possibility, ranging from a simple problem with the cover panel to a component approaching its operating limit. Valves are even more difficult to monitor because their movements are brief and occur only when the direction of flow must change. In good condition, a valve opens or closes at the correct moment, creating a sealed path between different branches of the system. After many cycles, its contact surfaces may wear down, deposits may form around the edges, or the actuator may respond more slowly. The valve may still move without reaching its final position, leaving a narrow opening through which fluid can pass. If it closes several seconds too slowly, two water streams that should remain separate may briefly mix. If it fails to seal completely, pressure may gradually decline without producing an obvious sign. Deposits can also hold the valve in an intermediate position, causing the system to receive less flow, even though the pump itself is operating normally. The data then shows weak water movement, but the cause lies not in the device creating pressure, but in a small gateway that has failed to open or close completely. Seals perform an even quieter role. They sit between joined surfaces, preventing liquids and gases from escaping through gaps nearly invisible to the eye. The material must remain soft enough to press tightly against each surface while enduring the temperature, pressure, and chemical composition of the fluid. After repeated heating and cooling, a polymer may harden, shrink, or lose its ability to return to its original shape. A leak may appear only when pressure rises, then disappear when the system returns to normal operation. There does not have to be a visible droplet floating through the compartment to reveal the problem. The amount of liquid lost may be too small to observe, or gas from outside the pipe may enter the water stream instead of water leaking outward. Gas bubbles cause pressure to fluctuate, change the sound of the pump, and make flow sensor readings unstable. The crew sees several symptoms across multiple devices, even though the original cause is only a seal that has lost its integrity deep behind a layer of insulation. Experience aboard the International Space Station has shown that small components, such as valves and seals, can determine the durability of an entire system. NASA has reported that some parts within the water processor assembly failed to reach their expected service life because of seal leakage and the effects of contaminants in the water stream. A microbial control valve also demonstrated lower reliability than anticipated once it entered real operation. In laboratory testing, equipment operates with predetermined water compositions, temperatures, and load cycles. Aboard the ISS, the waste stream changes with the people, materials, and activities inside the station. Small differences between a simulated environment and a real mission can cause a seal that performed well during testing to deteriorate more quickly, or allow deposits to affect a valve in ways never included in the original scenarios. These failures do not disprove the capability of the system. They simply remind us that reliability can never be determined completely before launch. A 2026 report on the thermal circulation pump assemblies aboard the ISS provides another important perspective. Of the 6 assemblies serving the same system, 3 had already been replaced, while 2 others were showing signs of deterioration. Although they shared similar designs and performed the same task of circulating water, they did not necessarily follow the same path toward failure. One unit showed changes in vibration, another consumed more electrical power, while a third gradually lost efficiency without stopping completely. Predicting failure based only on operating hours was no longer enough, because 2 pumps that had run for similar lengths of time could still have experienced different loads, temperatures, and fluid compositions. Engineers had to monitor several signs at once to estimate remaining service life, rather than waiting for a fixed milestone and replacing every unit on schedule. Sound and vibration become valuable sources of information in this situation. When a bearing wears down, a shaft becomes slightly misaligned, or an impeller encounters uneven fluid flow, the vibration pattern may change before performance declines noticeably. Accelerometers mounted on the pump housing record movements too small for a person to feel, while software compares them with data collected during earlier months. A newly appearing frequency may suggest where an unusual load is developing, while stronger vibration at a particular speed can indicate that a shaft or bearing is no longer balanced. The crew may also hear larger differences, especially after becoming familiar with the spacecraft's normal rhythm. Sound, however, is never a complete answer. A loose panel, a pipe touching the wall, or a change in pressure can produce similar noises, forcing the crew to compare them with temperature, electrical current, and flow data before reaching a conclusion. Electrical consumption provides another clue. A healthy motor requires a relatively stable amount of power to produce a given flow rate. When friction increases, deposits obstruct the impeller, or a pipe becomes narrower, the device must draw more current to maintain its speed. Yet a higher reading does not identify the exact cause. The change may begin inside the pump, but it may also come from a dirty filter downstream or a valve upstream that has not opened fully. A motor being forced to work harder is not necessarily the component that needs replacement. If the crew looks only at electrical demand and concludes that the pump has failed, they may remove a perfectly functional unit, while the true obstruction remains hidden deeper inside the plumbing. Diagnosis begins by combining several signs into a single story. Reduced flow indicates that water is no longer moving through the system as it once did. Higher current shows that the motor is carrying a greater load. Elevated temperature suggests that more energy is being lost as heat, while a change in vibration may point toward a rotating component. If pressure before the pump is normal but pressure after it is low, the problem may lie inside the unit itself. If pressure rises upstream of the filter, the restriction is more likely to be located beyond the pump. Data from valves, water quality sensors, and maintenance records continue narrowing the possibilities. The work resembles following a trail of evidence more than reading an error message, because the spacecraft does not always know which component is weakening. It only knows that the behavior of the entire network is no longer the same. The crew may perform tests by briefly changing the operating mode. Reducing pump speed and observing the pressure response can reveal how the system is behaving. Redirecting the water through a backup branch can show whether the problem lies in the primary line. A filter may be isolated from the loop so that the pressure difference across it can be measured, while a valve may be commanded to open and close several times to test its response speed. Every test consumes time, electricity, and part of the equipment's remaining life. Some procedures also require water processing to be temporarily suspended, allowing the clean reserve to begin falling while the crew searches for the cause. Testing for too long reduces the safety margin, but deciding too quickly creates the risk of repairing the wrong component. Replacing a pump is not as simple as removing the old unit and attaching a new one. The system must be isolated from the surrounding branches, pressure must be reduced, and the water remaining inside the pipes must be controlled so that it does not escape into the cabin. Panels, insulation, and connectors are removed within a confined space where tools and fasteners must be secured to keep them from floating away. After the new assembly is installed, the crew must check for leaks, purge gas from the liquid line, and gradually increase power to avoid creating a sudden pressure change. During this time, the affected processing branch remains offline, forcing the backup system or the clean water reserve to carry the remaining demand. More important still is the value of the replacement unit taken from storage. On the ISS, another assembly may be delivered on a future resupply mission if operational needs and launch schedules allow. A spacecraft traveling to Mars will not have that option. A spare used today disappears from the rest of the journey, while the newly installed unit immediately enters the same environment that weakened the original one. If the true cause lies in deposits inside the pipe, a stuck valve, or a shared design flaw, the replacement pump may soon begin showing the same symptoms. The crew will have lost one layer of protection without correcting the underlying problem. A diagnostic mistake does not necessarily cause an immediate disaster. The new pump may improve the flow for several days because it operates more efficiently than the old unit. The display returns to normal, making the replacement appear to have been the correct decision. If the pipe is gradually narrowing, however, resistance will continue to increase, and the readings will begin to deteriorate again. The crew must then face a more difficult question. Is the new assembly also failing, or was the original problem never inside the pump at all? Every removal and installation creates another opportunity to damage a connector, introduce gas bubbles into the system, or weaken the seal around a joint. A repair intended to restore reliability can sometimes add new points where future failures may begin. To reduce this risk, the spacecraft must monitor equipment health long before performance falls to a critical level. Temperature, electrical power, vibration, and operating time are stored as a continuous history, allowing software to compare the current condition with data from months earlier. Instead of waiting for a single measurement to cross a threshold, the system searches for trends appearing in several places at once. Longer pump cycles, rising temperature, and filters requiring earlier replacement may all point toward growing resistance. A change in vibration while flow remains stable may suggest that a mechanical problem is only beginning. Early detection gives the crew more time to conduct tests, prepare spare parts, and choose a repair window while water reserves and electrical power still provide a comfortable margin. Predictive capability, however, is always limited by the quality of the data. A temperature sensor may gradually drift, making the motor appear to be heating up even when its true temperature has not changed. Electrical interference may cause the pump load to look unstable. Deposits on a flow meter may produce readings lower than reality, creating a picture almost identical to a blocked pipe. When several indicators change together, the system tends to assume that the fault belongs to the equipment being monitored. Yet every conclusion passes through sensors that are exposed to the same heat, vibration, radiation, and aging as the surrounding hardware. The engineer still keeps a hand against the panel, listening to the deeper sound of the pump within the quiet cabin. The data is not yet strong enough to declare that the unit is failing, but it no longer matches the baseline recorded near the beginning of the mission. The crew can continue monitoring it, adjust the operating mode, or prepare a more detailed inspection. Each choice carries its own cost. While the spacecraft must continue maintaining water, air, and temperature for everyone living inside. A weakening pump often leaves traces in temperature, electrical demand, and vibration before it stops completely. These signs allow the crew to see the deterioration hidden behind the metal housing, but they do not come directly from the device itself. Everything must be measured, converted into signals, and displayed on a screen. If the component doing the observing begins to age alongside the component being observed, the distinction between a weakening pump and an inaccurate sensor gradually becomes harder to recognize. The question is no longer simply whether the spacecraft carries a spare. The greater concern is whether it still knows exactly which component must be replaced before the crew uses the only replacement they have. Two results appear almost simultaneously on the water control display. A sensor at the end of the treatment cycle indicates that the water meets the required standard and can be transferred into clean storage, while an instrument on the neighboring branch still detects a value above the permitted limit. The difference is small, just enough for the automated system to hold the water back rather than release it into the distribution network. On another data panel, the reported flow rate remains normal, even though the pump is consuming more electricity than it did the week before. The motor temperature rises steadily after each cycle, yet the pressure at both ends of the pipe remains almost unchanged. Each number can still be explained on its own, but when placed together, they no longer form a consistent picture of the system's true condition. No screen displays a warning that a sensor is lying. The measuring device does not know that it has drifted away from reality, and the computer can only process the signals it receives. The crew sees values presented with several decimal places of precision, but that appearance of accuracy does not guarantee that they reflect what is truly happening inside the pipes. A number can be displayed clearly, repeated consistently, and still remain wrong in the same direction for weeks. Once the data can no longer be trusted completely, the technical problem quickly becomes a crisis of perception. The spacecraft continues gathering information, but it is no longer certain which parts of that information should be believed. Sensors rarely move directly from working properly to falling completely silent. Before they stop transmitting signals, they may pass through a long period of decline while still appearing normal on the surface. A measured value may slowly drift away from the truth, respond to changes more slowly than before, or develop noise under certain conditions. A surface exposed to water may become coated with deposits, causing the instrument to take longer to recognize changes in chemical composition. Heat from a nearby motor can alter the behavior of electronic components, while radiation in space may introduce small errors into processing circuits. Prolonged vibration can affect connectors, moisture may enter poorly protected areas, and sensing materials can gradually age after thousands of operating hours. None of these causes must stop the device immediately, but each can widen the distance between the displayed reading and the system's actual condition. Slow drift is especially difficult to detect because it creates no obvious jump. If a temperature sensor reports a slightly higher value each week, the system may interpret the change as a natural variation in the environment. If several devices are exposed to the same heat or radiation, they may even drift in the same direction, preventing comparisons between them from revealing the problem. Two readings that agree do not necessarily mean that both are correct. The sensors may have been calibrated against the same degraded reference, coated by the same kind of deposit, or exposed to the same condition that pulled their results away from reality. Redundancy has real value only when the devices do not share the same source of error. In another situation, the sensor does not drift steadily but responds more slowly than the process itself. Water that has not yet met the required standard passes the probe, but for several minutes, the signal continues to reflect the clean water that came before it. The system believes conditions remain stable and allows a routing valve to open, while the newly arrived water, not yet fully tested, begins moving toward storage. By the time the sensor finally responds, that water may already have mixed with the clean supply, making it harder to isolate. The device still produces an accurate reading when given enough time, but its delay has exceeded the operating rhythm for which the system was originally designed. A seemingly minor loss of response speed can throw the control sequence of the entire network out of synchronization. An error in the opposite direction can also have significant consequences. A sensor may report that the water still fails to meet standards even after treatment is complete, forcing the flow back through the cycle. The crew may see this as the cautious choice, since additional treatment appears safer than accepting water of uncertain quality. Yet the extra loop keeps the pump running longer, exposes the filter to more contaminants, and consumes additional electricity. The heat produced must be removed by the cooling system, while less time remains for the cycles that follow. If the false signal continues, healthy equipment will age more quickly while trying to solve a problem that does not actually exist. When two water quality sensors produce conflicting results, the crew cannot simply choose the more reassuring number. They need to determine which device can still be trusted, but the answer often requires a third measurement. A water sample may be removed and tested manually with an independent kit, helping distinguish a faulty sensor from water that truly fails to meet standards. This method provides valuable evidence, but the number of test kits aboard is not unlimited. Every use consumes chemicals, test strips, or instruments that were expected to last for many more months. If sensor disagreements become frequent, the supply of testing materials will decline faster than planned, forcing the crew to decide which cases are serious enough to justify an independent confirmation. Repeating the entire treatment cycle also cannot become the default response to every conflict in the data. In the short term, it protects the water reserve from possible contamination, but the burden is transferred to equipment life and other resources. Pumps rotate longer, filtration membranes collect more material, valves open and close more often, and treatment chemicals continue to be depleted. If the water truly fails to meet standards, that additional use is necessary. If the fault lies in the sensor, the spacecraft is wasting the durability of its systems in response to a false signal. Both possibilities are reasonable, and neither choice is completely free of risk. Accepting the result from the sensor judged to be more reliable requires the same careful consideration. Engineers may use operating history, calibration records, and the location of each instrument to determine that one sensor has probably become coated with deposits. The water is then transferred into clean storage to avoid an unnecessary repeat cycle. If the judgment is correct, the spacecraft saves electricity, time, and filter life. If it is wrong, water that does not meet safety standards enters the distribution network and mixes with the treated supply, turning a local problem into a threat to the entire reserve. Every decision places finite resources on one side of the balance and the crew's safety on the other. Conflicting measurements do not always come from within the same system. Increased electrical consumption by the pump suggests a rising mechanical load, yet the flow sensor continues to report normal water movement. A higher motor temperature leads engineers to suspect friction or resistance inside the piping, while pressure readings show no significant change. If they look only at power consumption, the cause appears to lie in the pump. If they trust the flow and pressure data, the device is still operating correctly. Another possibility is that the power meter is experiencing interference, the temperature sensor has drifted, or the actual water flow has declined without the flow meter recognizing it. The numbers that were meant to narrow the list of causes now open the door to even more possibilities. The crew can compare the data with the equipment's sound and vibration, but these physical signs are not entirely clear either. A deeper motor hum could come from a wearing bearing, gas bubbles in the fluid, or a cover panel that was not secured tightly after being reinstalled. Increased vibration may originate in the pump, or it may be transmitted through the spacecraft's frame from a fan or another device. Direct inspection requires opening the wall panels, temporarily shutting down the system, and placing a crew member inside a confined area where every action carries the possibility of creating another fault. Discovering the truth about a sensor may require the crew to interfere with the very system they are trying to protect. Calibration can restore confidence when an instrument has drifted only slightly. The sensor is compared with a known reference, and the software adjusts its readings to compensate for the error. This process is accurate only if the reference remains stable and the cause of the drift does not continue changing. A surface coated with deposits may become clean after flushing, only to collect the same material again if the source has not been corrected. A component exposed to excessive heat may drift farther each week, forcing calibration to be repeated more and more often. Eventually, continually correcting the number is no longer safe enough, and the sensor must be replaced. But that decision still consumes a spare part that cannot be replenished. In orbit near Earth, conflicting data can be sent to the ground, where teams of specialists analyze it together. They have time to review the operating history, compare it with previous failures, and build a step-by-step sequence of tests. The crew receives guidance almost in real time, performs one action, and waits for confirmation before continuing. On the way to Mars, that approach is no longer practical. The distance between the two planets changes constantly, and a signal may take anywhere from several minutes to more than 20 minutes to travel in each direction. Near the greatest separation, a question sent from the spacecraft may require almost half an hour to reach Earth, and the reply may take roughly the same amount of time to return. A conversation that seems simple could last nearly an hour. The crew transmits data and reports that the motor temperature is rising, then waits while the pump continues to operate. By the time engineers on Earth receive the information, the condition they are viewing already belongs to the past. They analyze it, recommend reducing the pump speed, and send their response. But when the instructions finally arrive, the crew may already have switched the system to a backup branch, or the data may have changed in another direction. Mission Control is no longer observing the spacecraft's present. It is always watching its past. That delay turns the crew into the true decision-making center of the mission. They still receive knowledge, models, and support from Earth, but they cannot wait for guidance at every step when an immediate response is required. Procedures must be prepared in advance, software must help compare multiple possibilities, and the people on board must understand the systems well enough to make their own choices while no answer is available. They are not simply following instructions. They must also decide whether the current situation still resembles the one described in the message they sent. When a response arrives too late, the best decision may be to disregard it because conditions aboard the spacecraft have already changed. Communication interruptions make the problem even more complex. The sun may move between Earth and Mars at an angle that disrupts the signal, or the communication equipment may need to be shut down temporarily because of a technical fault. The crew must be prepared for periods when no advice can be received even as the problem continues developing. The spacecraft needs the ability to store data, analyze trends independently, and recommend safe actions within predetermined limits. Software can assign probabilities to different causes, but probability cannot replace human judgment when the input sensors themselves are under suspicion. An automated diagnostic system usually relies on relationships among different measurements. If flow decreases while electrical current rises, the software may suspect increasing resistance or a weakening pump. If water quality changes after a filter has reached the end of its expected service life, it may recommend replacing the filter. That logic works well when the data reflects reality. A faulty sensor can lead the model to a conclusion that is reasonable but incorrect. The more strongly the software trusts inaccurate measurements, the more convincing its recommendation becomes, because every step of the reasoning remains consistent with the original input. The mistake lies not in the algorithm, but in the foundation of information it was given. This is why the spacecraft needs several methods of verification that do not depend entirely on the same type of sensor. Water flow can be evaluated through a direct flow reading, the time required to fill a tank, and the pump's electrical consumption. Motor temperature can be compared with the temperature of the outgoing fluid, vibration levels, and operating load. Water quality is not judged only through continuous sensors but is also confirmed periodically with manual samples. When independent methods all point in the same direction, confidence increases. If they all depend on the same probe or electrical circuit, their agreement may only reflect a shared failure. Not every source of data deserves equal trust at every stage of the mission. A sensor calibrated recently may be given greater weight than one that has been operating for a long time. A probe known to experience interference when cabin temperature rises must be treated cautiously under similar conditions. The software monitors the history of each sensor, not only its current value, to identify which devices often respond slowly or tend to drift after long periods of use. The spacecraft gradually builds a health record for the very components responsible for observing its health. Even with automated support, the final pressure still falls on the crew. Prolonged uncertainty creates a different kind of fatigue from a clearly defined emergency. When an alarm sounds, everyone knows that a specific procedure must begin. Conflicting data provides no such boundary. The crew must continue daily life, monitor the readings, debate possible causes, and make decisions without knowing whether the problem truly exists. Their minds must hold several scenarios at once, ranging from a sensor with simple surface contamination to the possibility that unsafe water has already entered storage. A wrong decision costs more than a few hours. Repeating a treatment cycle shortens filter life. Opening the system for inspection may weaken a seal, and replacing the wrong sensor consumes a spare. If the crew becomes too cautious, resources will be used faster than planned. If they grow accustomed to false alarms and begin ignoring them, a real failure may be dismissed as noise. Balancing vigilance with conservation becomes part of survival, especially when every crew member knows that anything used today cannot simply be sent from Earth. Fatigue also affects how people interpret data. After many hours of testing, they may focus on the first hypothesis and search for numbers that support it. If they have encountered a weakening pump before, a newly appearing sound may immediately be assigned the same cause, even when the current problem lies in a sensor. Another crew member may believe that deposits have formed on the probe because that happened in the past. Both have reasonable grounds, but memory and experience can narrow their perspective instead of expanding it. Diagnostic procedures must force the crew to consider opposing possibilities, even when those alternatives are less convenient than the original explanation. Inside the cabin, light from the screens reflects across data panels that refuse to agree. The pump continues turning behind the wall, water keeps moving through the treatment stages, and the clean reserve remains sufficient for several more days. Nothing calls for panic, but time is not entirely on the crew's side. Every additional cycle consumes part of the equipment's remaining life, while every hour of delay may allow a real problem to spread if one is already developing. They decide to collect a manual water sample while slightly reducing pump power and redirecting part of the flow through the backup branch. The independent test result will not appear immediately, but it will provide another source of information that does not depend on the two disagreeing sensors. The data is packaged and transmitted to Earth with a detailed description, while the temporary decision must still be made on board. Mission Control will respond later, but the spacecraft cannot stop sustaining life while it waits. When the manual test confirms that the water meets safety standards, the sensor reporting contamination becomes the primary suspect. The crew can flush it, recalibrate it, or replace it if the error continues. The problem appears to have narrowed, but another question quickly emerges. What coated the sensor's surface and caused it to respond so slowly? Mineral deposits are a familiar possibility, but warm, damp pipes containing small amounts of organic matter can also create an environment favorable to something more complex. The spacecraft is cleaned before launch, but it is never completely sterile. Microorganisms travel with human beings on their skin, inside their bodies, in food, and across the surfaces of equipment. When they find water, nutrients, and a suitable place to attach, the walls of a pipe are no longer merely lifeless passageways. A very thin living film can begin to form, enough to distort a sensor's readings before anyone realizes that a tiny ecosystem has appeared inside the system. Before launch, every compartment aboard the spacecraft is cleaned according to strict procedures. Surfaces are wiped with disinfectants, equipment is inspected, food is sealed, and the initial water supply is treated to reduce the number of microorganisms carried on board as much as possible. From the outside, the spacecraft may appear to be an environment separated from the biological complexity of Earth. Yet, it can never become completely sterile, because life boards the spacecraft with the crew. Bacteria live on the skin, in the mouth and digestive system, on clothing, in food, and within the smallest gaps of equipment. Most of these microorganisms do not cause disease, and many have lived alongside the human body for a very long time. But when water, organic matter, and a suitable surface come together inside the same enclosed environment, they can begin building a new habitat behind the walls. The inside of a pipe is not as perfectly smooth and clean as the surface of new material may appear. Under a microscope, even a precisely manufactured surface contains tiny grooves, uneven points, and areas where the flow is weak. Water passing through carries extremely small amounts of organic compounds, minerals, and microbial cells. Most continue downstream and are eventually treated, but some manage to attach themselves to the wall. At first, that bond is weak, and the flowing water may wash them away. Under favorable conditions, however, the microorganisms begin releasing adhesive substances around their cells, helping them remain in place and protecting them from the surrounding environment. From a few scattered cells, a small community gradually forms on a surface designed only to carry water. This community is known as a biofilm. The name may make it sound like nothing more than a thin layer of grime, but its structure is far more complex. The microorganisms do not remain exposed on the pipe wall. They are surrounded by a matrix they produce themselves, made of water, complex sugars, proteins, and material drawn from the environment. This matrix retains nutrients, slows the penetration of disinfecting chemicals, and protects the cells buried deeper inside. Bacteria floating freely in the water are usually exposed directly to treatment agents, while communities living within a biofilm may endure harsher conditions because the outer layers absorb the effects first. A biofilm does not grow into a thick layer overnight. In its earliest stage, it is so thin that it has almost no effect on flow and produces no obvious change in sensor readings. Water continues moving at a normal rate, valves keep opening and closing, and microbial test results may remain within acceptable limits. Over weeks or months, the attached surface expands, more organic material becomes trapped, and layers of cells begin building on top of one another. The water no longer touches the pipe wall as it did at launch. Instead, it moves across an increasingly uneven surface, where biological patches create small eddies and gradually increase resistance. The flow does not necessarily decline all at once. The pump may compensate for the new resistance by running longer or consuming more electricity. The system still completes its cycles, allowing the biofilm to continue growing unnoticed. Where the flow is slower, perhaps in a corner or behind a valve, more nutrients remain behind, giving the microbial community an even better opportunity to expand. Biological change begins to affect the mechanical system, while the mechanical response alters the biological environment in return. A pipe once viewed as a passive channel gradually becomes a place where a living structure is growing inside. The first effect may appear on a sensor. A probe must remain in direct contact with the water to measure temperature, electrical conductivity, or chemical composition. Once a biological film coats its surface, the device no longer senses the true water stream immediately. It receives the signal only after it has passed through this new layer of material. Its response becomes slower and may sometimes be pulled away from the true value by substances trapped within the biofilm. Electrically, the sensor still functions. It continues transmitting data and reports no internal error, yet the surface connecting it to the environment has changed. The spacecraft is now looking at the water through a window that is no longer completely clear. Valves are also vulnerable to accumulation within narrow gaps. The edge of a valve must press tightly against another surface to stop the flow, but biofilm can grow around this contact area, trapping deposits and preventing the mechanism from sealing completely. At first, the opening may be too small to create an obvious pressure loss. Over many cycles, fluid leaking through that point changes the shape of the film and carries more material into an area that is already difficult to clean. The valve may begin responding more slowly, become stuck between positions, or require greater force to complete its movement. The control system sees that opening and closing times are increasing, but it cannot easily determine whether the cause lies in the motor, mineral deposits, or biomass growing inside. A filter may seem like the ideal barrier for preventing the problem from spreading, yet the filter itself provides an enormous surface area for microorganisms to occupy. Fibers, small pores, and layers of material designed to capture impurities also create many regions of slow flow where organic matter can collect. When biofilm forms across the filter, resistance rises, and the pump must generate more pressure to push water through. Replacing the filter removes the biomass growing there, but it does not eliminate communities already attached to pipes, storage tanks, or upstream valves. The new filter may soon become contaminated again by fragments released from somewhere else in the system. A biofilm does not remain permanently attached to its original surface. As the layer thickens, its outer portion is exposed to the force of flowing water and may break away in small pieces. These fragments travel through the system, sometimes becoming trapped in a filter, sometimes lodging inside a valve gap, and sometimes attaching to a new location. An area that previously had no problem may receive a large number of microorganisms within a short period. A downstream sensor may suddenly report a change, leading the crew to believe the contamination has just begun, even though the true source may have been developing quietly elsewhere for months. Its ability to trap contaminants makes biofilm a problem that extends beyond the microorganisms themselves. Organic compounds, minerals, and metal particles can become embedded within its structure. Conditions at the surface may therefore differ from those in the water flowing past it, creating localized chemical environments that were never anticipated in the original design. Some microorganisms make the surrounding area more acidic or produce metabolic compounds that affect metals. Over time, the surface beneath the biofilm may begin corroding at small points that are difficult to detect during ordinary inspection. At first, the corrosion only makes the material slightly thinner, but it also creates new irregularities where the film can attach more firmly, allowing the process to reinforce itself with every cycle. NASA treats biofilm as a practical concern for space-based water systems because its effects are not limited to water quality. During the history of orbital operations, biological buildup has contributed to clogged pipes, obstructed valves, and difficulties within equipment assemblies connected to water. These cases do not mean that every pipe aboard a spacecraft will quickly become covered, but they demonstrate that microgravity does not prevent microorganisms from forming communities on surfaces. Water remains water, materials continue, providing places to attach, and substances released by human beings still supply nutrients, even in very small amounts. Microgravity also makes the growth of biofilm more difficult to predict. On Earth, gravity influences how particles settle, where gas bubbles move, and how liquids form layers. In space, particles do not naturally fall to the bottom of a tank, while gas bubbles may remain in places different from those expected under familiar conditions. Regions of weak flow develop according to pipe geometry, surface tension, and pump activity. These conditions create new attachment points that ground testing cannot reproduce completely. A system that performs well in a laboratory may still develop a different pattern of accumulation after many months in orbit. Disinfecting chemicals are one of the main methods used to control microorganisms, but the dosage must always remain within a careful balance. Too little will fail to control a growing community, while too much may make the water unsuitable for drinking or damage seals, filtration membranes, and other materials. Disinfectants are also consumed when they react with organic matter, which means the concentration measured in the tank may not match the concentration deep within the narrow spaces of a biofilm. The outer layer may absorb most of the treatment, while cells buried inside survive and rebuild the community once conditions become favorable again. NASA and other research teams have explored several approaches to reduce dependence on any single method. Silver-based disinfectants can control microorganisms in water, but they must be maintained at the proper concentration. Material surfaces can be modified to reduce initial attachment, making it harder for microorganisms to establish a stable foundation. Flushing cycles can be designed to generate enough shear force to remove buildup before it becomes thick. Ultraviolet light can damage microbial genetic material as water passes through an illuminated chamber, reducing reproduction without adding large quantities of chemicals to the entire system. Each solution still carries its own limitations. Ultraviolet light is effective only when it can reach the microorganisms, while cloudy water, deposits, or a thick biological layer may shield what lies beneath. Lamps gradually lose intensity and require electricity to operate. Anti-adhesive materials may become less effective after their surfaces are scratched or coated by other compounds. Flushing consumes clean water, energy, and chemicals, and it may detach pieces of biofilm without destroying them completely, allowing them to travel elsewhere. No method can turn the water network into an environment that remains lifeless forever. The realistic goal is to keep biological growth below the level at which it threatens crew health or hardware performance. Experiments aboard the ISS continue examining how ultraviolet radiation, new materials, and microgravity affect biofilm formation. The value of this research lies not only in finding stronger antimicrobial treatments. Engineers need to know where microbial communities begin, how their growth rate changes with fluid flow, and which signs appear before the pipes are noticeably affected. If vibration, flow, and water quality sensors can recognize a characteristic pattern of change, future spacecraft may be able to intervene earlier, before an entire pipe assembly must be removed and cleaned. The most difficult problem is that the signs of biofilm closely resemble many other failures. Reduced flow may be caused by a weakening pump, a dirty filter, a valve that has not opened completely, gas bubbles in the waterline, or a sensor reporting a value lower than reality. A change in electrical conductivity may come from the chemical composition, an error in the probe, or material trapped within the biological film. Rising pressure ahead of a filter suggests resistance, but it does not reveal whether that resistance comes from mineral deposits, solid particles, or microorganisms. The crew cannot see through the pipe wall to identify the cause. They receive only indirect symptoms from instruments that may themselves be coated with biofilm. Imagine that the flow through one treatment branch begins to decline very slightly. The pump draws more electrical current, and each cycle takes longer to complete, while the final water quality continues to meet requirements. Based on the history of equipment wear, the crew suspects that the pump assembly has begun to age. A slight increase in vibration and a deeper sound seem to support that conclusion. After reviewing the procedure, they decide to use the backup assembly, shut down the treatment branch, and remove the old unit from the water line. The new pump is installed, the system is purged of gas, and leak checks are completed. When operation resumes, the flow increases, cycle time becomes shorter, and electrical demand returns close to the expected level. Every initial sign suggests that the repair has succeeded. The old assembly is inspected, but no obvious damage is found, something that can be explained by deterioration appearing only under real operating loads. The crew records the incident, updates the maintenance schedule, and continues the mission, believing they have found the cause. A few days later, the flow begins to decline again. At first, the change is smaller than before and may be interpreted as the new equipment settling into normal operation. By the following week, the pump must run longer to complete the same cycle. Electrical demand rises, while the pressure difference across one section of piping gradually increases. The backup assembly remains healthy, but the resistance downstream was never removed. Biofilm has narrowed the flow path, and the new pump only concealed the symptom temporarily by generating stronger pressure. The decision to replace the equipment was not technically unreasonable. Every sign was consistent with a weakening pump, the procedure was performed correctly, and the system genuinely improved after the repair. The mistake was that the deeper cause had not been recognized. The spacecraft used an important spare, accepted additional risk during removal and installation, and left the buildup inside the pipe untouched. Without an independent method of inspection, the crew may begin to suspect the new assembly, the sensors, or the quality of the replacement part, while the microbial community continues growing beyond their sight. The situation becomes even more difficult when biofilm affects the sensors at the same time. A partially coated flow probe may report a value lower than reality, making the decline appear more severe. A slow-responding water quality sensor may force the system to repeat treatment cycles, increasing pump operating time and sending more nutrients through the affected pipe. The crew sees rising electrical demand, falling flow, and longer processing times, 3 signs that all appear to indicate a mechanical failure. In reality, the mechanical system is suffering the consequences of a biological problem, while the measuring equipment distorts the picture even further. Cleaning pipes deep within the system is not as simple as replacing a filter. Chemicals must remain in contact with the entire surface long enough to work, including narrow spaces that are difficult for the flow to reach. The concentration must be strong enough to break apart the protective film while remaining within the limits the materials can tolerate. After treatment, the system must be flushed to remove the remaining chemicals, consuming a significant amount of clean water. If the biofilm detaches in large fragments, downstream filters may clog quickly, or valves may receive additional debris. The cleaning process addresses the current danger, but it also places a temporary load on a network already experiencing wear. Future piping designs must account for inspection and accessibility from the beginning. Sections that are too long, too narrow, or filled with dead zones will be difficult to clean once a microbial community has formed. Connections that allow individual sections to be removed make repairs easier, but they add more seals and potential leak points. Smoother internal surfaces reduce places where organisms can attach, but they cannot eliminate organic matter completely. Stronger flow limits accumulation, yet it requires larger pumps and more electrical power. Every engineering solution involves a trade-off among mass, energy, complexity, and maintainability. Human beings are also inseparable from the problem. Diet, medication, health, and hygiene habits influence the compounds entering the wastewater. The microorganisms carried by the body change over time inside an enclosed environment, while communities within the cabin may adapt to the spacecraft's unusual conditions. Not every microorganism needs to be eliminated. The goal is to prevent harmful species or biofilm-producing communities from growing beyond control. Attempting to destroy all life could require excessive quantities of chemicals, damage materials, and still fail to provide a permanent solution. Microorganisms must be monitored in much the same way as pump vibration. Regular water samples reveal the number and types of organisms present, but they do not fully represent communities attached to pipe walls. Flowing water may contain very few cells, while a biofilm continues growing strongly on the surface. Only when part of it breaks away does the measured count suddenly rise. Monitoring must combine water samples, pressure changes, flow trends, and sensor behavior to detect accumulation before it becomes an obstruction. Inside the equipment compartment, the pipes still show no obvious outward sign. Their exterior metal surfaces remain clean. The temperature stays within limits, and no droplets leak into the cabin. Inside, a thin film continues trapping organic matter, spreading around valve gaps, and slowly covering the probes. The pump responds by running longer. The sensors respond with increasingly delayed readings. The filter responds with a growing pressure difference. No component has failed completely, yet the entire system has begun adapting to the presence of a living community that no one can see. A weakening pump can be replaced, a drifting sensor can be recalibrated, and biofilm can be cleaned or controlled through chemicals, ultraviolet light, and changes in flow. When each problem appears on its own, the crew still has a chance to identify it and respond with the proper procedure. The greater danger emerges when they arrive together, because mechanical decline slows the flow and encourages accumulation. The biological film distorts sensor readings, and the inaccurate data leads to decisions that force the pump to operate even longer. From that point forward, each fault begins to conceal the cause of another. The spacecraft is no longer dealing with one failed device, but with an entire chain of changes reinforcing one another. While water continues to flow, the pump continues to turn, and the readings remain close to the safe range. A disaster does not need to begin in a single dramatic moment. It can take shape through many small deviations, connected for long enough to erode the remaining safety margin before any alarm begins to sound. The water flow drops by less than 2% during the first cycle. The difference is so small that the system does not classify it as a fault, because the crew's daily demand changes and every measurement carries some degree of uncertainty. The pump automatically extends its operating time to compensate for the shortfall, allowing the amount of clean water returned to storage to remain on schedule. On the display, the final result gives no reason for concern. The tank is replenished to the expected level. Pressure remains within limits, and no warning appears. Judged only by the outcome, the system has completed its task as usual. Beneath that apparent stability, however, the way the spacecraft produces the result has begun to change. The pump needs more time to move the same amount of water. The electrical current through the motor is higher than before, and slightly more heat is being generated inside the equipment compartment. The cooling system absorbs that additional heat and carries it to the radiator, so the cabin temperature has not changed enough for the crew to notice. The added load is distributed among several different devices, preventing any single component from experiencing a dramatic increase. The spacecraft preserves normal conditions by consuming a little more energy, time, and mechanical life. Automatic compensation is one reason a complex system can continue functioning when one component begins to weaken. If the flow rate declines, the pump runs longer. When heat rises, the cooling loop increases its output. If a filter creates more resistance, the control system compensates with greater pressure. These adjustments prevent the crew from having to respond to every minor fluctuation, but they also conceal the early stages of a developing chain of deterioration. The final result remains stable while the internal cost continues to rise, much like a body maintaining its normal rhythm by forcing healthier organs to work harder. After several weeks, the longer operating time causes the filter to process more water than expected. Contaminants accumulate faster, the pressure difference across the filtering material gradually increases, and the pump must generate still more force to maintain the flow. A regulating valve downstream opens and closes more frequently to stabilize the pressure, increasing the number of mechanical cycles beyond the original plan. The cooling system receives additional heat not only from the motor but also from the extended operation of the surrounding equipment. The intervals between maintenance procedures begin to shorten, even though each one occurs only a few days earlier than expected. No component has failed completely. The filter still captures contaminants, the valve still changes position, the pump continues turning, and the water at the end of the cycle still meets quality standards. Yet the entire network must work harder to preserve the same result. No spare part has been used, the water reserve has not fallen sharply, and the crew continues its normal routine, but the safety margin has already begun disappearing in the form of additional operating hours that can never be recovered. The onboard engineer notices the trend while comparing data from several weeks. Average flow has been declining slowly, while the pump's electrical current has been moving in the opposite direction. The pressure difference across the filter has also increased, although it has not yet reached the replacement threshold. No single measurement clearly identifies the cause. The pump may be aging, the filter may be collecting contaminants faster than expected, or deposits inside the pipe may have narrowed the flow path. Biofilm growth is also considered, but water samples have not revealed abnormal microbial levels. The data suggests that resistance is increasing somewhere within the system, yet it does not reveal the exact location. The crew begins with the least invasive solution. Using a procedure prepared before the mission, they flush the suspected branch by sending water and cleaning chemicals through it long enough to remove deposits and weaken any buildup on the interior surfaces. This approach does not require the pump to be removed or the equipment assembly to be opened, reducing the risk of leakage and avoiding the use of a major spare part. In exchange, the clean water used for flushing does not immediately return to storage, while the cleaning chemicals are taken from supplies intended to last throughout the mission. Once the system has been flushed and returned to operation, the flow improves noticeably. The pump completes each cycle more quickly, electrical demand falls, and the pressure difference across the treatment branch returns close to its earlier level. These results strengthen the theory that deposits or buildup inside the piping were the primary cause. The crew records how much water was used, updates the chemical inventory, and adjusts the monitoring schedule to detect any sign of recurrence. The intervention is considered successful because the system recovered without requiring the replacement of a critical equipment assembly. The improvement lasts for several weeks, then slowly begins to disappear. Flow declines again, more gradually than before, but in the same direction. The pump once more requires additional power. While the flow sensor reports values that remain close to normal, the pressure difference no longer rises as steadily as it did before, weakening the theory that the pipe is simply becoming narrower. The sensor may have drifted away from the true value, the buildup may have been removed only partially, or the pump may now be deteriorating internally after operating under increased load for so long. The flushing procedure improved the system, but it did not prove that the underlying cause had been eliminated. The conflicting data makes every option more costly. If the flow sensor is trusted, the pump is still moving enough water, and the higher electrical demand may simply indicate an aging motor. If electrical consumption and cycle time are trusted instead, The real flow is encountering resistance that the sensor has failed to detect. Replacing the sensor would consume a spare part and require a brief shutdown. Replacing the pump would be an even more significant decision because the backup assembly is intended for a later stage of the mission. Flushing the system again might provide temporary relief, but it would consume more water and chemicals. The crew tries to narrow the possibilities by redirecting the flow through an auxiliary branch and changing pump output within safe limits. The readings still do not fully agree. Flow responds more slowly than expected when motor speed increases, but pressure data reveals no clear obstruction. The pump housing is warmer than its baseline temperature, while vibration has changed only slightly. The data is transmitted to Earth, but communication delay means the ground team always sees the spacecraft as it was many minutes earlier. While they wait for a response, the water system must continue processing the waste produced by the crew each day. After reviewing the operating history, the onboard engineers decide to open the equipment assembly for direct inspection. The affected treatment branch is isolated, pressure is reduced, and the water flow is temporarily redirected through a lower capacity backup system. Removing the panel changes the airflow inside the equipment compartment, while moisture released from the lines is controlled with local extraction equipment. Every connector is labeled, tools are secured with tethers, and the work area must remain clean to prevent additional dust or microorganisms from entering the open system. During the repair, the spacecraft's ability to recover water from cabin humidity declines. Water vapor released through the crew's breath and skin continues to accumulate, causing the average humidity to rise slightly. The ventilation system distributes this moist air throughout the compartments, while the thermal control system adjusts to limit condensation on cold surfaces. The temporary shutdown of a single water processing branch has already begun affecting the air and thermal loops, even though the original problem remains inside the equipment compartment. The clean water reserve is sufficient to sustain operations for several days, but it falls more quickly while recovery capacity remains limited. The crew adjusts daily routines to extend the safe repair window. Personal hygiene is reduced, some research activities that require water are postponed, and meals are selected according to how little water they need for preparation. Exercise must continue to protect muscles and bones, but the schedule is rearranged to avoid having several people generate large amounts of heat and moisture at the same time. The oxygen generator is also placed in a conservation mode, because electrolysis depends on clean water. Stored oxygen remains plentiful, and no one is in immediate danger, but the control system begins prioritizing the most essential functions. Activities that can wait are temporarily suspended, while the supply inventory is reviewed to determine how long the spacecraft can maintain this condition if repairs take longer than expected. The failure has not moved beyond control, but it has already escaped the boundaries of the water system and begun shaping the daily life of the entire crew. When the pump assembly is opened, no component is found broken or burned. The shaft remains intact, the impeller shows no obvious damage, and the seal has not developed a leak large enough to explain the full change. A thin layer of buildup is discovered on several surfaces, but it is not enough to identify it as the only cause. The flow sensor is tested separately and found to respond more slowly than the standard, although its error remains close to the acceptable limit. Each finding explains part of the problem, but none is large enough to account for all the symptoms. This is when the chain of deterioration becomes most difficult to recognize. The pump may have lost some efficiency after operating under high load for so long. Buildup remains inside the pipes after the first flushing procedure. The sensor's delayed response hides part of the true decline. The filter is becoming dirty faster than normal, while the regulating valve has endured additional opening and closing cycles. No fault is severe enough on its own, but together they create a system that is becoming increasingly difficult to maintain. The crew cleans the pump assembly, replaces a seal showing signs of hardening, and recalibrates the sensor. After the system is reassembled, leak testing takes longer than expected because gas bubbles appear in one section of the waterline. The bubbles must be removed slowly to avoid creating pressure fluctuations, extending the shutdown even further. The clean water reserve continues to fall, cabin humidity remains above normal, and daily operations stay under conservation measures. When the primary branch starts again, the flow improves, but does not return to the level seen at the beginning of the mission. The pump's electrical demand falls slightly, while the recalibrated sensor produces more stable readings. The system is operational, yet no one knows how long it will remain in this condition. Buildup still exists inside sections that cannot be reached, and the recently serviced pump assembly has endured another removal and installation. Every measurement is better than before, but the distance from perfect condition remains. After consulting with the ground team, the crew decides to activate the backup assembly to reduce the load on the repaired system. This unit was originally reserved for a later stage of the mission, after the primary equipment had completed several more months of operation. It remained isolated from the water flow most of the time to preserve its service life, starting only periodically to confirm that it was still ready. That plan must now change. The backup assembly begins operating steadily. Flow returns to the expected level, processing time becomes shorter, and the clean water reserve begins to recover. Cabin humidity falls as full water recovery from the air is restored. The oxygen generator leaves conservation mode, and normal hygiene and research schedules gradually resume. The crew rests after several days of continuous monitoring, while the sound of the newly activated pump flows evenly behind the wall. No one has been injured. There has been no fire, no compartment has lost pressure, and the spacecraft remains on course for Mars. Judged only by its present condition, the crisis is over. Water continues circulating, oxygen is being produced, and every living condition has returned to the safe range. Yet, the spacecraft after the repair is not the same as it was before the problem began. Some of the flushing chemicals have been consumed, the water reserve fell lower than planned, and many hours of service life were taken from the cooling system, fans, and valves while they compensated for the decline. The sensor has been recalibrated, but it is no longer new. The serviced primary assembly is now held in reserve, while the unit originally intended for the future must carry the daily workload. The spacecraft remains functionally healthy, but its protective structure has changed places. The layer of redundancy that once rested untouched in storage is now turning with the water flow, exposed to the same heat, vibration, and chemical conditions as the previous equipment. If the failure occurs again, the crew no longer has an unused assembly ready to activate immediately. They may return to the original system, perform a deeper repair, or replace internal components, but fewer options remain. The idea of redundancy often creates the impression that two identical devices provide two completely independent chances. When the primary unit fails, the duplicate takes over, and the problem is solved. Reality is more complicated because assemblies sharing the same design often share many of the same weaknesses. They are made from similar materials, use the same kinds of seals, process the same water, and operate in the same thermal environment. If the cause is an unusual deposit, biofilm, or an unexpected contaminant, the backup unit will be exposed to the same threat as soon as it enters service. A common cause failure can weaken several layers of protection through a single underlying problem. 3 identical pumps do not provide 3 entirely separate options if all of them are vulnerable to the same type of particle in the water stream. 2 sensors built to the same design may both be affected by heat or radiation. Multiple seals made from the same material may age in similar ways when exposed to a compound that was never anticipated. Adding more equipment still provides additional time, but it does not guarantee that the cause that weakened the first unit will disappear. One way to reduce the risk of common cause failures is to use different technologies for the same function. One branch might process water through one method, while another relies on a different mechanism. 2 sensors may measure the same variable using separate physical principles, making them less likely to fail in the same direction. Backup equipment may use different materials or operate under conditions unlike those of the primary system. This diversity provides stronger protection against unknown causes, but it also requires the spacecraft to carry additional types of spare parts, tools, and specialized supplies. The crew must also learn how to operate, inspect, and repair several different technologies rather than one standardized design. Control software becomes more complex, the number of valves and connections increases, and every new interface creates another potential location for a leak or an installation error. The system requires more mass and volume, taking space that could otherwise hold reserve water, food, or scientific equipment. A solution that reduces one kind of risk may create another at the same time. This is the paradox at the center of long-duration spacecraft design. A simple system contains fewer components, fewer connections, and fewer operating modes, reducing the number of points that can fail. Yet, when an unexpected condition appears, it also offers fewer alternate routes and fewer ways to adapt. A complex system provides more options, allowing the crew to isolate a faulty branch, switch to another technology, or preserve a function through a temporary operating mode. But every added option requires its own valves, sensors, software, and maintenance procedures, increasing the number of components that can deteriorate. No design can be completely free of risk. An immortal spacecraft would require so much mass, energy, and redundancy that it could never be launched. The realistic goal is to keep possible failures within a range where the crew still has time to recognize them, enough supplies to respond, and more than one path for returning the system to a safe condition. Reliability does not come from a promise that equipment will never fail. It comes from the ability of the mission to continue after some of its original assumptions are no longer true. During the days that follow, data from the backup assembly is monitored closely. Electrical current, temperature, vibration, and pressure differences are compared with the early operating history of the original unit. If the same trend appears, the cause is more likely to lie in the shared environment or design than in the isolated wear of one device. The crew also collects water samples more frequently, checking for microorganisms, chemical composition, and signs of deposits. Every test reduces uncertainty, but it also consumes limited supplies. The spacecraft cannot remain under intensive monitoring forever. The crew's time must also be devoted to operations, research, exercise, and rest. If maintenance consumes too many hours, the ability to complete other mission objectives declines, while fatigue increases the risk of human error. In this way, a chain of technical failures can spread into human performance even while the living environment remains within safe limits. Eventually, the crisis fades without a clearly defined moment of resolution. There is no single second when everyone looks at the display and knows that the danger has disappeared. The data simply becomes more stable, the water reserve begins rising again, and the normal schedule is restored piece by piece. The sound of the pump once more becomes part of the familiar background, but the crew no longer hears it in the same way. Every small change in vibration receives more attention because they now understand that the spacecraft's present stability depends on equipment once reserved for the future. They have repaired the failure, or at least returned the system to a manageable condition. The spacecraft still has water, electrical power, oxygen, and the ability to continue its journey. What has been lost does not appear on a screen as a warning. It exists in the partially emptied chemical container, the reduced number of test kits, the additional operating hours accumulated by the machinery, and the backup assembly now running earlier than planned. The safety margin has not disappeared completely, but it has become thinner. If the same chain of deterioration returns, the crew will still have options, though fewer than before. The original system can undergo a deeper repair. Smaller components can be replaced, or the pipes can be cleaned through a more aggressive procedure. Each option will require more time, more supplies, and greater precision than the first response. The next crisis has not yet arrived, but the spacecraft's ability to withstand it has already changed. Every life support system can carry backup pumps, replacement sensors, additional filters, and emergency bypass lines. No spacecraft has enough mass to carry a complete duplicate of itself. As those protective layers are gradually used, the final repair workshop no longer exists inside the equipment storage area. It exists in the crew's ability to transform whatever remains into a new solution. Before launch, a small compartment aboard the spacecraft became the physical result of thousands of decisions about the future. Its racks were filled with filters, seals, valves, wires, connectors, sensors, circuit boards, tools, and larger equipment assemblies wrapped and secured for storage. Every item had a reason to be there, but each one also meant that something else had to remain on Earth. An additional kilogram of spare parts does more than occupy space in a storage compartment. It increases launch mass, raises fuel requirements, and reduces the room available for food, water, scientific equipment, or radiation shielding. The spacecraft cannot be filled with a duplicate of every component, while no one can know exactly which failures will occur after many months of operation. Selecting spare parts is not as simple as bringing the components that have failed most often aboard the International Space Station. A Mars spacecraft will have a different design, operate for a longer period, and be unable to receive regular resupply missions. A component that rarely fails on the ISS may become a weak point when required to operate continuously in a new environment. By contrast, a part that needed frequent replacement in low Earth orbit may have been improved before an interplanetary mission begins. Engineers must predict the future using incomplete data, then turn that prediction into a supply list constrained by mass. Every choice is a trade-off among the likelihood of failure, the consequences if the part cannot be repaired, and the possibility of using the same spare across several systems. One approach is to carry complete equipment assemblies. When a pump, processing unit, or control panel develops a fault, the crew isolates the affected branch, removes the old assembly, and installs a replacement in the same position. This kind of repair is faster, reduces the number of steps required in microgravity, and limits the need to diagnose the failure down to individual components. Standardized connections make the process resemble replacing a sealed box. Once the crew has checked for leaks and restored power, the system can return to operation without requiring them to open a motor, solder a circuit, or handle extremely small parts. That convenience comes at the cost of mass. A large assembly contains many components that may still be functioning perfectly and can be removed from service simply because a small internal valve no longer seals properly or a control board has lost one signal channel. The healthy parts leave the system along with the failed component, while the spare inventory loses a heavy unit that could only be carried in very limited numbers. If the same failure happens again, the crew may keep the original assembly and recover parts from it. But opening hardware that was never designed for onboard repair will be far more difficult than replacing the entire module in the first place. The other approach is to carry a larger selection of small, interchangeable components. Seals of the same size can serve several valves, standardized motors can be used in different pumps, and electronic boards can be designed in modules so that one section can be replaced without discarding the entire assembly. This method makes better use of mass and allows a compact spare parts inventory to address a wider range of failures. A container holding dozens of seals takes up far less room than a complete pump, while standardized connectors may allow the crew to build a bypass when the original configuration is no longer suitable. In return, the repair work becomes more complex and more vulnerable to error. Replacing a seal requires opening the assembly, removing the correct layers, cleaning the surfaces, checking for scratches, and installing the new part with the proper amount of tightening force. A motor must be aligned correctly to avoid vibration. Electrical wires must be connected with the proper polarity, and sensitive circuit boards must be protected from static electricity. In microgravity, screws do not fall to the floor, but may drift into ventilation gaps. Drops of fluid escaping from a pipe do not flow downward but gather into floating masses around nearby surfaces, while tools must remain tethered at all times to keep them within the work area. Every additional step creates another opportunity to install something incorrectly, damage a connector, or produce a leak that did not exist before the repair. The best spare parts strategy probably lies somewhere between these two extremes. Critical assemblies that must be restored quickly can be carried as larger modules, while less urgent equipment can be designed for repair with smaller components. Interchangeable parts are prioritized to reduce the number of different supplies required, while lightweight components that are difficult to manufacture on board can be stored in greater quantities. This approach requires the entire spacecraft to be designed for maintenance from the beginning. Panels must be easy to open. Connectors must remain accessible. Pipes need clearly defined isolation points, and the software must help the crew understand the exact configuration of the system after every modification. A device designed only to operate efficiently may not be suitable for a long journey. If it is buried behind several layers of material, uses multiple types of fasteners, or requires tools available only on Earth, the practical reliability of the entire system declines, even if the component itself has a very long service life. On a mission without resupply, repairability becomes part of performance. A durable component that cannot be reached may be more dangerous than one that wears out sooner, but can be replaced within a few hours. Even with careful preparation, the crew may encounter a failure that matches nothing in the spare parts inventory. A support bracket may crack in an unexpected location. A cover may deform after being removed several times. A connection may need to transition from one size to another, or a standard tool may be unable to reach a fastener hidden behind a pipe. These problems do not require a new motor or a complicated circuit board. They require an object with the correct shape, enough strength, and the ability to be produced aboard the spacecraft. This is where onboard manufacturing begins to reveal its value. In 2014, the design for a wrench was transmitted from the ground to the International Space Station as data, then manufactured by a 3D printer on board. That event did not turn the ISS into a complete factory, but it demonstrated that not every tool has to be selected before launch. Instead of carrying every shape that might be needed in the future, a spacecraft can carry raw material and manufacturing equipment, while designs are stored in a library or created when a problem appears. Data has almost no meaningful mass, while the physical object is produced only when it is truly needed. During a long mission, a printer could create brackets, handles, protective covers, cable clips, adapters, short sections of tubing, or tools customized for locations that are difficult to reach. If a plastic fastener breaks, the crew would not need to dismantle an entire assembly simply to recover one small part from another module. They could measure what remains, select a suitable design, and manufacture a replacement. When a standard tool is too long or difficult to control in microgravity, a new version could be created with tether points, a shorter handle, or a different angle of access. This capability is still limited by the materials carried on board. A printer that uses polymers cannot produce precise copper windings, semiconductors, high-performance magnets, or complex chemical sensors. Even with plastic components, strength depends on print orientation, temperature, the quality of bonding between layers, and the type of load the part must endure. A bracket holding electrical cables does not require the same standard as a connector placed inside a pressurized water line. A component that looks complete to the eye may still contain small gaps, weak layer bonds, or a surface that is not sufficiently sealed for a life-critical system. Printed objects must be inspected before being installed in an important location. The crew must evaluate their dimensions, surface quality, strength, and ability to tolerate heat, sometimes using test samples printed at the same time to confirm the quality of the material batch. If a component will come into contact with drinking water, the material must not release harmful compounds. If it will be placed near electrical equipment, it must withstand operating temperatures without creating an additional fire hazard. Every new manufacturing capability requires its own quality control procedures, because producing the wrong spare part on board is no better than carrying the wrong one from Earth. The supply of raw material is also finite. Polymer filament, metal powder, or feedstock for other manufacturing technologies must all leave Earth with the spacecraft. Once that material has been used, the ability to return it to a usable form depends on the recycling system. Old components can be ground down and manufactured again, but material quality often declines after repeated cycles unless the process is carefully controlled. Contamination can alter strength, while different colors or types of polymer cannot always be mixed together. Onboard manufacturing makes the spare parts inventory more flexible, but it does not turn raw material into an endless resource. While the printer produces needed components, monitoring duties can be shared with robots. NASA has developed programs intended to increase autonomous maintenance capabilities aboard space stations during periods of limited communication or when no humans are present. The Astrobee robots aboard the ISS have been used as test platforms for moving through the cabin, recording images, recognizing their surroundings, and assisting with inspections. ISAC is intended to combine robots, sensors, and software so that future habitats can monitor equipment with a greater degree of autonomy. A robot flying through the cabin does not become tired from repeating the same inspection route every day. It can pass through an equipment compartment while the crew is sleeping, record the sound of a pump from the same position, photograph a control panel from the same angle, and use a thermal camera to search for unusually warm areas. When these records are compared over many weeks, small changes in sound or temperature may become visible before a person notices them. The robot can also check whether a storage bag is blocking a ventilation opening, search for a reflective droplet hidden inside a gap, or read the position of a valve in a location that is difficult to inspect regularly. Its greatest value does not lie in replacing humans for every repair, but in creating a consistent history of observation. People usually pay closer attention when they already have a reason to suspect a problem, while an automated system can collect data even when everything appears normal. The sound of a pump today can be compared with its sound 3 months earlier. The shape of an insulation panel can be examined across hundreds of images, and the temperature of a connector can be tracked through every operating cycle. Silent deterioration becomes easier to recognize when the spacecraft possesses a detailed memory of itself. The robot can still become another machine that requires maintenance. Its thrusters, cameras, batteries, processors, and movement systems all experience wear. If one of its sensors begins to drift, the monitoring data also becomes less reliable. A free-flying device must avoid colliding with the crew, cables, and sensitive areas. It needs electrical power for charging, a place to dock, and software safe enough that it does not create additional work for the people on board. When it encounters an obstructed location or a situation that was never included in its programming, the robot may provide only an image without understanding the meaning of what it sees. Data from the spacecraft and its robots can be entered into an engineering replica commonly known as a digital twin. This is not simply a three-dimensional image used for observation, but a model intended to reproduce how the real system responds. The model's pump contains information about flow, temperature, electrical demand, and wear. Its pipes have resistance, its valves have response times, and its filters have estimated service lives. New data continuously adjusts the model so that it reflects the spacecraft's current condition more closely, rather than preserving only the configuration it had on launch day. Before closing a real valve, the crew can test the action in the digital twin to see how pressure might change in other branches. If the primary pump is shut down, the model can estimate how quickly the clean water reserve will decline and how hard the backup system must operate. When a sensor reports a rising temperature, the software can compare several possible causes that might produce the same sign, then suggest tests capable of distinguishing among them. Instead of intervening directly through trial and error, the crew gains a space in which to examine the consequences beforehand. The digital twin can also help estimate remaining service life. If a motor begins consuming more electricity, vibration increases, and cycle time grows longer, the model may predict how long the equipment can continue operating before the risk exceeds an acceptable level. The crew can then choose a maintenance window when the water reserve is high enough, the work schedule is less demanding, and the backup assembly has already been tested. Repair no longer exists only as a response after failure appears, but becomes a process that can be prepared in advance. The model still cannot understand the spacecraft correctly when its input data is wrong. A flow sensor coated with deposits may lead the digital twin to believe that the pump is weakening. If two probes drift in the same direction, the model may become even more confident in the wrong conclusion because the data sources appear to agree. Phenomena not represented in the software, such as biofilm growing in an unexpected location or a material reacting with a new substance, can cause the real spacecraft to behave differently from the simulation. A digital twin represents only what humans have learned how to include within it. The unknown remains outside every equation. The crew must understand the model deeply enough not to treat its predictions as absolute commands. Its results should be regarded as one more source of evidence, considered alongside direct observations, physical samples, and the system's operating history. If the software predicts that a pump has 30 days of service life remaining, but its sound changes rapidly within a few hours, the crew must know when to trust the new physical evidence over the model. When a sensor is under suspicion, they must adjust the confidence assigned to its data rather than allowing the automated system to continue reasoning from an uncertain foundation. The spare parts inventory can also be managed like a living system. Software tracks the location, quantity, and material age of each item, along with components that can be shared among several systems. When equipment begins to deteriorate, The spacecraft does more than predict when it may fail. It also checks whether the correct spare is still available, whether enough printing material remains, and which tools will be required for the repair. If one seal can serve 3 different systems, using it today must be weighed against the risks facing the other 2. Supplies are no longer a static list, but a network of choices that changes after every repair. When the exact spare is unavailable, the crew must find a way to transform existing components into a temporary solution. A motor from a less critical device may be transferred to a life support pump if its voltage, power, and connections are compatible. Water may be redirected through a backup line, even if the resulting flow is lower than the original design intended. A sensor from a research branch can be used to inspect the primary system, while an inoperative circuit board may be dismantled so that its unaffected components can be recovered. These changes gradually move the spacecraft away from its original design, making it essential to document every modification accurately so that future repairs are not based on outdated diagrams. Interchangeability works only when it has been planned in advance. Standardized connectors, common voltages, and modular interfaces allow components to move between systems. Highly specialized designs may provide better performance for individual devices, but they also make the spare parts inventory heavier and reduce the crew's ability to improvise. A long-duration spacecraft may need to accept slightly less optimization in exchange for greater repair flexibility. A shared motor may be larger than necessary for some devices, but its value increases when it can replace several different components. Repair instructions must also extend beyond expected procedures. The onboard library needs to contain diagrams, 3-dimensional models, material data, and a complete history of every maintenance action. Artificial intelligence can help locate the appropriate steps, warn that a connector remains pressurized, or identify compatible parts in storage. A display worn in front of the technician's eyes could mark the position of fasteners, show the direction of removal, and present the correct connection sequence, reducing the risk of overlooking a step in a confined space. These tools support memory and reduce cognitive strain, especially when the crew is tired or repairing equipment outside their original area of expertise. No matter how broadly they are trained, no crew member can become the deepest expert in every field. The medical officer may need to help inspect an electrical board. A software engineer may take part in repairing a water line, and a pilot may have to evaluate the quality of a printed component. Communication delay prevents them from waiting for every small instruction from Earth. Knowledge must be stored aboard the spacecraft in a form that is easy to locate, easy to understand, and flexible enough to apply to a configuration that has changed through repeated repairs. Extended maintenance also affects physical and psychological health. Working for hours in a fixed posture under microgravity causes fatigue, while knowing that the final spare part is being used makes every movement feel more consequential. Crew members must check one another's work, rest at the proper times, and prevent urgency from creating new mistakes. The final repair shop requires more than tools. It also needs procedures that protect human beings from exhaustion, because a trembling hand, fading attention, or a rushed decision can turn a repairable component into one that is completely lost. A robot can hold a light, position a camera, and bring tools to the work area. Software can display each step. A printer can create a clamp that was never carried on board. A digital twin can predict how pressure will change after a valve is closed. Yet no technology can take complete responsibility for the decision. The person performing the repair must still confirm that the surface is clean, the seal is seated correctly in its groove, the connection has been tightened with enough force, and the system responds normally when restarted. These small details often remain beyond the model's ability to evaluate completely, especially after the hardware has been modified several times. The fundamental limits become clearer after every repair. Robots require batteries, printers need raw material, sensors require calibration, and software depends on accurate data. The more complex an autonomous system becomes, the more components it adds that must also be maintained. Technology helps the crew use resources more intelligently, but it cannot create matter from empty space. When the last spool of polymer is gone, the printer becomes a machine without material. Once the spare circuit board has been used, A library of designs cannot turn data into semiconductors. When electrical power must be prioritized for life support, robots and manufacturing equipment may be shut down at the very moment the crew needs them most. Inside the equipment compartment, an open assembly lies before the crew. The correct replacement part is not in storage, but a seal of nearly the right size is found in a non-essential system. The printer produces an additional retaining ring to compensate for the small difference, while a robot illuminates the work area and records the entire procedure. Before installation, the component is measured, pressure tested in a small model, and its material is inspected. The digital twin predicts that the system can operate at reduced capacity if the flow path is adjusted. None of these solutions matches the original configuration, but together, they create a path safe enough for the mission to continue. After startup, pressure rises slowly. The engineer watches the repaired connection, another crew member monitors the data on the display, and the robot records thermal images. Water begins flowing through the necessary branch, at a lower rate than before, but with stable performance. The spacecraft has not been restored to perfect condition. It has only been repaired enough to preserve the cycle and give the crew more time to find a lasting solution. This may be the true image of repair on the way to Mars. There will not always be a perfectly matched new component, a complete procedure, or a team of specialists standing just behind the crew. They must combine the remaining spare parts, digital designs, manufacturing materials, monitoring robots, and accumulated experience to create a solution that was never written before launch. They become electricians when a circuit board loses a signal, plumbers when a valve no longer seals, software engineers when the model no longer matches the data, and quality control specialists when a new component has just emerged from the printer. Technology can help the spacecraft hear a pump changing its sound, predict that a filter is aging, and test the consequences of an action before it is performed. It expands the available options, reduces the number of spare parts that must be carried, and helps the crew perform work beyond their original specialties. Even so, every solution remains limited by the materials, electrical power, time, and human strength that left Earth aboard the spacecraft on launch day. The final repair shop is not located within a single room. It is distributed across every device that can be dismantled for parts, every remaining spool of material, every model stored inside the computer, and the knowledge of the people living on board. Once the final layer of redundancy has been used, the ability to continue the journey depends on how well they still understand the spacecraft and how long they can transform what remains into a functioning system. Technology helps the spacecraft recognize that it is growing weaker, but no printer, robot, or software can erase the fundamental limits of the mission. Everything inside must still survive on the matter and energy that left Earth on the day of launch. In the end, the question is not only whether the crew can repair the equipment, but how much capacity the spacecraft will still have after each repair to face the failure that comes next. After everything we have explored, the question that seemed so simple at the beginning of the journey has become much harder to answer. Pumps must continue turning. Fans cannot remain stopped for too long. Sensors must preserve their accuracy. Water lines must resist deposits and biofilm. Filters must maintain their efficiency, and seals must remain tight after thousands of thermal cycles. Any one of these components could become the first point of weakness, but there is not enough scientific evidence to say with certainty that one specific part will always fail first aboard every spacecraft bound for Mars. The reason is that such a spacecraft does not yet exist as a complete vehicle, and no crewed mission has spent several years traveling through deep space. What we know today comes from the International Space Station, ground-based testing, uncrewed missions, engineering models, and technologies that are still being developed. The ISS has shown that pumps can deteriorate, valves can stick, seals can leak, sensors can drift, and microorganisms can form films inside water systems. Yet the ISS operates close to Earth, receives regular resupply missions, and has a structure different from that of a future interplanetary vehicle. Its data reveals real patterns of risk, but it cannot become a precise prediction of which component will stop working first. The spacecraft's design will also determine which parts experience the greatest stress. A water system built around many small distributed pumps will face different risks from one that depends on only a few high-capacity assemblies. If sensors use several independent measuring principles, a drifting probe may be detected sooner. If the pipes are made from materials that resist attachment and remain accessible for cleaning, biofilm will have less opportunity to become a serious problem. The mission may be the same, but two different architectures can produce completely different chains of failure. Crew size, daily routines, and mission duration also change the operating environment. The amount of wastewater depends on the number of people on board, their diet, health, and physical activity. Oxygen demand rises on days of intense exercise. Air quality is affected by cabin layout, the materials in use, and equipment opened during the journey. The spacecraft does not operate under fixed conditions like a machine inside a laboratory. It lives alongside human beings, and those human beings continually change the conditions the system must manage. If we had to identify a group of likely candidates, moving components would often appear near the top of the list. Pumps and fans must rotate for thousands of hours while enduring friction, heat, and vibration. Bearings can wear down, lubricants can change, and motors may require more electrical power to produce the same result. These devices also work in environments where the water or air is never perfectly clean. Deposits, dust, gas bubbles, and small changes in pressure can all create loads different from those anticipated in the original design. Valves and seals are also easy to overlook because they are small, yet they perform essential tasks. A valve must open at the correct moment, close completely, and maintain its response speed through countless cycles. A small deposit along its edge, or a slowing actuator, may allow water to leak into the wrong branch. A seal creates no large movement, but it must preserve its elasticity under changing temperatures, pressures, and chemical conditions. As the material hardens or deforms, a leak may appear without producing any visible drop of water. Filters and treatment membranes do not rotate, but they accumulate traces of everything that passes through them. Impurities, organic compounds, microorganisms, and mineral deposits gradually fill their small openings, increasing resistance and reducing efficiency. They are usually replaced according to a schedule, but that schedule is based on assumptions about the quality of the incoming flow. If the wastewater composition differs from expectations, a filter may reach the end of its service life much sooner. A motionless component still ages by holding more and more material within itself. Sensors deteriorate in a less intuitive way. They may continue transmitting data regularly even after their readings have begun drifting away from reality. Deposits can coat the probe's surface. Electronic components can be affected by heat or radiation. Response times may become slower, and noise may appear within processing circuits. When a sensor stops completely, the failure is usually easy to identify. The more dangerous condition is when it remains stable enough to be trusted while its error has already grown large enough to influence operational decisions. Water lines may become the setting for a long biological process. Deposits and biofilm narrow the flow path, trap contaminants, coat sensors, and interfere with valves. Pumps must operate longer to overcome the resistance, gradually turning a biological problem into mechanical wear. If the crew replaces only the pump or filter without removing the cause inside the piping, the symptoms will soon return. Electronic equipment must also survive in an environment very different from a control room on Earth. High-energy radiation can affect memory, processing circuits, and sensitive components. Most critical systems will be shielded, designed with error correction, and built from more radiation-resistant hardware, but every layer of protection adds mass and cost. A single event may temporarily alter data, while accumulated radiation exposure can degrade components over time. Treatment chemicals, disinfectants, and polymer materials are not permanent either. Solutions can lose concentration. Catalysts can become less effective. Adhesives and coatings can age, and soft materials can turn hard or brittle. Some spare parts may remain untouched in storage while still experiencing the same passage of time, temperature changes, and radiation as operating equipment. When they are finally needed, they may no longer be exactly as they were on launch day. The list of candidates could continue, but the component most likely to fail first is not necessarily the most dangerous one. A sensor may stop working and be replaced within minutes. A filter reaching the end of its service life may already be part of the maintenance schedule. The primary pump may stop, while the backup assembly takes over exactly as designed. In these cases, the first failure does not push the mission toward disaster. It simply confirms that the spacecraft is operating as a system built to be repaired and renewed. The real difference lies in what remains after that repair. A spare part has left storage. A new filter has begun counting down its own service life. The supply of flushing chemicals has decreased, and the replacement equipment has entered the same environment that weakened the original component. The crew has spent many hours on maintenance, while other systems have worked harder during the shutdown of the primary branch. The failure has been corrected, but the spacecraft has not returned to its previous condition. It continues the journey with fewer options. This is why the first thing to fail may not be best understood as a specific component. What disappears first may be the safety margin of the entire system. The safety margin is not contained inside a box, nor does it appear as a component with its own identification number. It is the distance between the spacecraft's present condition and the point beyond which it no longer has enough capacity to recover. When the water reserve remains high, backup equipment is unused, sensors are trustworthy, and the crew has enough time to rest, that distance is wide. A failure can still be isolated, tested, and repaired without placing immediate pressure on the other life support cycles. That distance narrows when water is lost faster than expected. Filters require early replacement, sensors become less reliable, or backup systems must enter service ahead of schedule. It shrinks further when shared spare parts are consumed, printing material runs low, manual test kits become scarce, and more of the crew's working hours are redirected from research toward maintenance. None of these changes creates a disaster on its own, but together they make the next failure harder to manage than the one before it. Human time is also part of the safety margin. The crew must sleep, exercise, monitor their health, prepare food, and complete scientific work. If the spacecraft demands constant maintenance, those activities begin to shrink. Sleep loss reduces concentration, prolonged stress affects judgment, and repair work becomes more vulnerable to mistakes. A spacecraft may still have enough spare parts, but if the crew no longer has enough time or strength to use them correctly, it is still approaching its limit. The reliability of information also determines the distance from danger. When sensors agree and manual samples confirm their readings, the crew can act with confidence. When the data begins to conflict, every decision requires more time, testing, and supplies. The spacecraft may carry enough pumps for replacement but still be unable to determine whether the pump is truly the cause. A spare part sitting in storage does not provide safety if the spacecraft can no longer identify where it should be used. The reserve margin can disappear without a single red warning appearing on the screen. The displays may still show enough water for many months, oxygen within acceptable limits, and a stable cabin temperature. The change exists in the number of seals remaining, the age of the backup pump, the amount of chemicals already consumed, and the number of hours the crew must devote to maintenance each week. The spacecraft remains healthy in the sense that it can still perform every essential function, but maintaining that health now requires more effort than it did before.